China, the biggest manufacturer in the world, and soon expected to have the largest economy of any country on the planet. But all that success brings with it a major challenge. China is a country with an unquenchable thirst for energy. Something engineer and Shanghai resident Yewande Akinola witnesses firsthand every day.
Living in downtown Shanghai, it's so easy to see how much energy is consumed on a daily basis. In this city alone, population has grown to 24 million people. That is why this country needs more energy.
China's traditional power stations burn as much coal as the rest of the world combined. But with fossil fuels a finite resource, China's engineers face a seemingly impossible problem. How to keep the lights on and China's dreams alive. Yewande is on her way to see how the Chinese are looking to their landscape to provide the solution.
China has the greatest hydropower potential, more than any other country in the world. There are 23,000 rivers in China, and the Yangtze River is the mightiest of them.
With a population of around 1.4 billion and rising, if hydropower is to be the solution, China has to think big. The Three Gorges Dam on the Yangtze is an epic engineering project of a scale never witnessed on planet Earth before.
It is just incredible.
It's more than 2 kilometers long, holds back a reservoir of over 1,000 square kilometers, and is the largest producer of hydroelectric power in the world.
The area is prone to catastrophic floods. To lessen the possibility of flood damage and to create a source of clean power, engineers have dreamed of building a dam like this for the last 100 years.
Construction is now entering its final phase. For Deputy Director of Construction Technology, Mr. Qihua Ding, it's the challenge of a lifetime.
I've been working here for more than 30 years. I think it's the greatest project I've ever seen.
In order to create such a seemingly impossible structure and harness the power of one of the world's largest rivers, engineers need to draw upon centuries of innovation. Humans and the odd animal have been building small dams since the dawn of history. In the ancient Middle East, they realized that dams could protect from floods in wet weather and store water in dry seasons. But China's Three Gorges Dam will eclipse anything ever built before.
The Three Gorges Dam is the biggest dam in the world. It has a quantity of more than 280 million cubic meters of concrete.
With tens of millions of people living further along the Yangtze, getting the build right is literally a matter of life and death.
With millions of tons of water pushing against the wall, the residents downstream are really depending on this wall to stay up. Any imperfections and the consequences could be catastrophic.
Such a feat of concrete construction would be impossible without one of history's great innovators. In the early 20th century, The parched American Southwest was becoming desperate for both water and power. It was a problem that would require an epic engineering solution. And Professor of Civil Engineering Andrew Smith is heading for a bird's-eye view of it.
Wow. This is the Hoover Dam. At the time of its construction, this was the world's largest concrete structure that had ever been built. Even today, roughly 80 years later, it takes your breath away.
The Hoover Dam was like nothing that had been built before.
Weighing in at 6.6 million tons of concrete, this was an unparalleled engineering marvel.
By attempting to tame the mighty Colorado River and harness the power locked within it, its engineers were setting themselves a seemingly impossible challenge.
The dam stands 700 feet tall and has a base thickness of 660 feet. The biggest problem and the biggest challenge was one of sheer scale.
The problem lies in the way that the chemical components of concrete react.
So what I have here is cement as well as water. And these are really the two main active ingredients in the curing process. Now, before it really starts to cure, let's quickly check the temperature. Before I dipped it into the concrete, the thermometer was already reading 44 degrees Celsius. Gives you an idea of how hot it is here.
It takes just half an hour for the temperature of the mix to reach its peak at 68 degrees Celsius.
So that's an increase from our original temperature of 24 degrees Celsius. And you could really, really feel the heat.
Engineers estimated that if they poured all the concrete in one go, it would take 125 years to cure and cool, meaning uneven setting and potentially catastrophic cracking. It was down to the project's general supervisor, Frank Crowe, to solve the conundrum. And what he came up with is still visible today in the old engineers' inspection tunnels, running deep within the dam.
So Frank Crowe, nicknamed here on the site Hurry Up Crowe, came up with an ingenious method for cooling the concrete to help it cure faster. The solution was to pass extremely cold water through 1-inch pipes. And the amazing thing is we can actually still see evidence of those pipes here.
In 1931, thousands of workers began constructing the dam out of a series of gigantic blocks. All the time cooling the concrete with ice-cold water, produced by a specially built refrigeration plant. And it worked perfectly. The whole job was completed in 1935, 2 years ahead of schedule. And the record-breaking dam even created a record-breaking body of water behind it.
This is Lake Mead. When the dam was erected, it became the world's largest man-made lake. At full capacity, they say, the volume of water could cover the state of Connecticut with 10 feet of water. As an engineer, this is an incredible sight to see.
Harnessing the power of the Colorado and the giant Lake Mead meant even now, over 80 years later, the Hoover Dam provides electricity to 3 states and brings light to some of the world's great metropolises. Impressive as the Hoover Dam is, the Three Gorges Dam is an incredible 5 times the size.
The height of the dam is 181 meters, and the total length of the dam is 2,309 meters.
The design requires almost 28 million cubic meters of concrete. In 1998, pouring begins. To accelerate the setting process and reduce risk of cracking, engineers take the techniques pioneered at the Hoover Dam to a whole new level. The ingredients are air-cooled even before they're mixed. High-speed conveyors take the concrete from mixing zone to site in just 15 minutes. And vast amounts of workers are used to pour an average of 20,000 cubic meters every single day.
In the peak period, more than 30,000 people took part in the construction.
Water cooling is supplemented with a mist sprayed over the working area to reduce the effects of the hot summer weather. The enormous concrete pour takes a total of 8 years.
In 2006, the whole dam was completed. It's the most important milestone of the project. Of course, I was very excited at that time.
But the engineers of the Three Gorges Dam project still have further challenges to face, and will have to turn to the great innovators of the past.
It's a 3-story high marvel of Victorian engineering.
To produce more impossible engineering. At over 2 kilometers long, the Three Gorges Dam in China is one of the most ambitious engineering projects ever attempted. Built to tame the regular floods that hit the Yangtze River and harness the clean hydroelectricity potential of China's largest waterway. Engineer and Shanghai resident Yoande Akinola has travelled to see firsthand how its creators are taking on this seemingly impossible challenge.
The Yangtze River is the 3rd largest and longest in the world, running at 6,400 kilometers. And the river is now the lifeblood for the thousands of people who live along it.
For Three Gorges engineer Qi Huading and his colleagues, completely blocking this busy and vital waterway is simply not an option.
The Yangtze River is the mother river of the Chinese people. It's the lifeblood of the people along this river. The cargoes passing through amounts 100 million tons per year.
To deal with the cargo ships, the Three Gorges team have employed a technique dating back to medieval times.
Here is the Three Gorges ship lock. It's the largest ship lock of this kind in the world.
The lock is more than 1.5 kilometers long and raises and lowers the river traffic 113 meters through 5 giant steps.
The ship lock is very busy. It works nearly 24 hours a day. And we take a very small time to maintenance.
But there's one element of this incredible engineering feat that doesn't suit all the vessels on the Yangtze.
It takes about 3 hours and 40 minutes or even 4 hours to pass through the ship lock.
Taking up to 4 hours to pass through the locks is simply too slow for the river's many passenger ships. So Mr. Ding and his fellow engineers face another gigantic conundrum. How can they get ships up and over the dam 8 times more quickly? Anderton, in the north of England. In 1870, designer Edwin Clark was employed to solve a particularly tricky problem. One that would be familiar to the engineers of the Three Gorges. He was asked to find a way to link the busy Trent and Mersey Canal with the adjacent River Weaver. A job desperately needed to speed up the journey times for barges carrying valuable commercial cargoes of salt.
This was a pretty stiff challenge for Clark in the late 1800s because the height between the canal and the river was about 50 feet. Transferring the salt from the canal to the river was time-consuming, laborious, and it was really slow. So Clark had to come up with an ingenious solution.
Almost a century and a half later, Dr. Rhys Morgan is still able to experience that solution himself.
Known as the Iron Spider, the Anderton is the oldest operating boat lift in the world. It's extraordinary. It's a 3-story high marvel of Victorian engineering. It's just fabulous.
Clark's mighty construction scooped up the barges and the water they were floating in and transferred them in one smooth action, 15 meters between the two levels. To do it, he used what was at the time a cutting-edge technology: hydraulics.
The basic principles of all hydraulic systems are defined by a law which was created by a French mathematician called Blaise Pascal. And it goes something like this. If you apply a pressure on a liquid in a closed system, then that pressure is distributed throughout the whole liquid in the system. And Edwin Clark used this to great effect with his boat lift at Anderton. He started off by making 2 watertight caissons. These are the tanks which held the boats and the water in which they floated. And he supported those caissons on top of 2 hydraulic rams. And there was a liquid in those rams and a pipe joining them both together. So as I exert some additional force to this hydraulic ram, I can start to see that the pressure is being pushed through the adjoining pipe and lifting up my other hydraulic ram. It's brilliant.
The design was genius in its simplicity. The 2 caissons were perfectly balanced, so all that was required to push the upper caisson down and so lift the lower caisson was an extra 5 centimeters of water. The result, an almost effortless rise and drop for up to 4 narrowboats simultaneously.
And most importantly, the journey time took less than half an hour, and that saved huge amounts of time and enabled the trade to be much quicker. It's just a fabulous piece of engineering. It's wonderful to be here.
Edwin Clark proved that moving boats between different water levels was no longer impossible, and his ingenuity inspired generations of engineers around the world. At the Three Gorges, in addition to the world record-breaking ship locks, its engineers are now in the process of creating a ship lift on an unparalleled scale. And Yawande is getting a unique opportunity to ride on it whilst it's still under development.
It's the weirdest sensation, it's really insane. It feels like I'm in a big, massive swimming pool and being pulled up many, many meters up, or in a lift with a massive pool in it, being lifted up. It's an engineering feat, a beauty in so many ways. And super impressive.
Capable of carrying a 3,000-ton passenger liner, This vertical ship lift consists of reinforced concrete towers which support the huge steel pool. Instead of hydraulics, the lift will use massive counterweights and pulleys to lift the 132-metre-long pool and the vessel floating in it a vertical distance of 113 metres.
I think it's the best ship lift in the world. The counterweight of the ship lift weighs nearly 16,000 tons. I think it's a massive achievement for the Gorges Dam.
This world record-breaking lift will solve the seemingly impossible challenge of transporting passenger ships across the dam without frustrating delays.
For the ship to pass through the ship lock may take much more long time. So the ship lift is the fastest way for the boat to pass through the dam. The Three Gorges ship lift is the biggest in the world right now.
To keep passengers happy, when this is complete, it will take only 30 to 40 minutes of travel time from top to bottom. Now, this is a brilliant solution.
But the engineers of this mighty project have yet further challenges to face, and will again need to draw from history's great innovators.
This is an amazing but quite terrifying experience.
To produce even more impossible engineering. The massive Three Gorges Dam in China. Stretching more than 2 kilometers across the Yangtze, it holds back a reservoir of over 1,000 square kilometers. One of its key functions is to reduce the risk of flooding in the region. Shanghai-based engineer Yowande Ekenola has traveled to Hubei province to see how the dam's team are taking on this seemingly impossible engineering challenge.
Every 10 years or so, the Yangtze River floods quite seriously. In fact, over the last 200 years, there have been over 200 catastrophic floods, which unfortunately have caused over 300,000 people their lives.
Dams can help control the effects of excessive rainfall, but extreme floodwaters can also cause dams to collapse, with catastrophic consequences. One problem is called tow scour, when water spills over the top of the dam and wears the foundations away.
Now, if we imagine a flood situation where we have lots and lots and lots of water flowing over this dam, we've got all that water hitting the bottom of the dam. As we can see here, the integrity of the dam becomes very questionable and it starts to collapse. So there it goes.
The consequences of the giant Three Gorges Dam failing are almost unimaginable. So, to reduce this deadly risk, its designers need to look to one of history's great innovations. In the 1930s, construction began on the first large-scale dam on the French River Dordogne. Engineer André Coyne was given the job.
This is an amazing but quite terrifying experience.
Dr. Rhys Morgan is getting up close and personal with the mighty Gorges Dam.
I'm here with this huge dam behind me, and I'm stood next door to this overflow channel, and luckily for me today, the gates aren't open, because if the reservoir was too high, the water was overflowing, then the gates would be opened and some 700 cubic meters per second of water would be gushing out, flowing down this spillway. And I'd probably be blown away just by standing here.
The Gorges Dam is 90 meters high. The power of an overflow thundering to the toe of the dam has the potential to destroy the foundations. But Coyne had an answer, and the secret lies halfway down the gorge.
This is a ski jump spillway, so called because it has a lip at the bottom, just like a ski jump. And the ski jump prevents that water carrying all the way down to the base of the dam, where it can seriously erode the foundations. Instead of carrying on all the way to the base of the dam, it gets flicked into the air, and all that water turns into droplets as it's mixed with the air, and the energy is dissipated.
The Gorges Dam holds back 47 million meters cubed of water in the reservoir above, and its Director of Engineering Projects appreciates just how important Coyne's design is.
The ski jump spillway is necessary for the water to be transferred from upstream to downstream. Otherwise, the water would overtop and overflow the crest of the dam and then impact the toe of the dam, which would undermine the foundation and generate the total collapse of the dam.
André Coyne's innovation was a major milestone in dam engineering, and his ingenuity and foresight opened up a whole new world of possibility for dam engineers. Coyne changed the way dams were designed forever.
The colossal Three Gorges Dam uses a series of 46 ski jump spillways. When reservoir levels rise and water needs to be discharged, gates are opened, and the pressure shoots the water 100 meters from the vulnerable foundations of the dam, at the same time dispersing its kinetic energy. For Deputy Director of Construction Technology, Mr. Qi Huading, the design is more than just practical.
The dam is a very beautiful structure, and the spillway looks like a piano.
When the spillways are in full flow, it's easy to see the potential energy locked within the Yangtze River. Chinese engineers want to capture it and turn it into electricity. But China is a country of around 10 million square kilometers, so the project needs to produce immense amounts of power.
I think the water power is very important to China because it's a very clean energy. The Yangtze River is a very big river, and we just get the disaster from this river. But now we can change the power energy into useful energy.
So how can engineers make the Three Gorges project the most productive hydroelectric power station on Earth? Man has always recognized the potential power of water for industry. Ancient miners built dams in order to collect water and then release a wave to scour the land. In the Middle Ages, Islamic engineer Al-Jazari designed dozens of ingenious water-powered devices, from irrigation systems to extraordinary clocks.
Have you got the time?
But it would be the Industrial Revolution that would take hydropower to another level. In 1834, British-born engineer James B. Francis arrived in the busy textile town of Lowell, Massachusetts.
At the time James Francis arrived here in Lowell,
Massive mills like this one were sprouting up all along the vast canal system. The mill complex ultimately would produce up to 160 miles of cloth every day. But the power began to run out.
With the industry's thirst for energy, the water in the canals became increasingly precious. It fell to James Francis to find a way to squeeze as much power as possible out of each and every drop.
The problem was that the mills here in Lowell were being driven by simple water wheel systems. These are relatively inefficient. They're driven by water falling into the buckets to make them turn, only using a portion of the energy available here in the canal system.
What Francis went on to design would change the world forever. And his original invention can still be found deep within the canal complex.
Wow. So this is it. This is the site of the very first James Francis turbine. The turbine is actually 5 meters below us. It's amazing to think that this turbine right here started the hydropower revolution.
James Francis took the idea of a water wheel and turned it on its side. He enclosed his turbine so water was in contact with the whole wheel constantly. And he added a series of vanes to direct the water at the optimum angle.
So here we have a deconstructed Francis turbine. This was actually one of the last turbines installed here at Lowell, and we can see how it works. So you can imagine the water would be guided in with directed vanes, then would hit these runner blades, and then if you watch here what happens, so as the water strikes the runner blades, it drops down and comes all the way out down below here. The sum total of all those enhancements led to nearly 90% efficiencies of the turbine.
It was so successful that even today, the Francis turbine is still the world's most used design.
Francis was a brilliant engineer who made a massive contribution to the Industrial Revolution.
The Three Gorges Dam is the biggest hydroelectric project of all time. So it's fitting that it should use the world's largest Francis turbines.
This is one of the 2 turbine buildings, and just listen to that. That is the sound of huge quantities of water traveling at up to 80 miles per hour, turning the 32 largest ever Francis turbines built.
Installing the giant turbines was an engineering feat in its own right. Each turbine weighs 450 tons, and the crane required to install them had to be factored into the design of the hall from the outset. And the UFO-like generators that convert the momentum of the turbines into electricity are some of the biggest of their kind.
These 450-ton turbines can generate the equivalent electricity of 25 million tons of crude oil, and wait for it, 50 million tons of coal.
The water enters through a series of huge inlets and falls 80 meters towards the Francis turbines, with a flow rate of up to 950 cubic meters per second. This torrent then rotates each turbine at 75 revolutions per minute, which in turn drives the generator above.
And each one of these turbines can, in a day, produce enough power to power over 16,000 TV sets. I think that is just amazing, really cool.
But generating the electricity is only one part of the challenge. The Three Gorges designers will still need to draw inspiration from history's greatest innovators.
Wow, this is truly awesome. We can see the nearly 170-foot drop.
In their quest to create their own modern marvel of impossible engineering. In 1994, work began on one of the most ambitious engineering projects of all time. China's colossal Three Gorges Dam is designed to combat catastrophic floods and produce vast amounts of hydroelectricity. But whilst its potential to produce energy is huge, the dam's location presents another seemingly impossible problem.
The dam is 1,000 kilometers away from Shanghai and other key industries lying in the east. Engineers needed a system that would deliver that energy huge distances with minimum losses.
And they wouldn't be able to do it without one of history's most extraordinary engineering dreamers. In the 19th century, distributing electricity was a big problem. But that would change when engineers decided to tap into one of the world's most awe-inspiring natural phenomena.
Here at Niagara Falls, 150,000 gallons per second pours over the top. 4 of the 5 Great Lakes of North America empty into the Niagara River and pour over the top of these falls into Lake Ontario to the north. As the water crashes over the top, all of the potential energy is converted into kinetic energy and comes down with tremendous force. Engineers knew that they could create a lot of electrical power with this. But the key challenge was not in creating the power, but in distributing it.
And if you know where to look, clues to how the challenge was overcome can still be seen more than a century later.
Wow, this is truly awesome. We can see the nearly 170-foot drop. That's the same drop as the Niagara Falls themselves, but we're over a mile away from the falls. And the water flowing through here right now is awesome.
Engineer Andrew Smith has tracked down the site of the Adams power plant, where tunnels redirected water from the Niagara River down this huge drop, driving electricity-generating turbines. Now, only one building is left standing on the site.
Wow. It may look like an old warehouse, but actually it's a really, really special place. This is the Adams Power Plant Transformer House.
In this building, history was made. And the man behind it was engineering genius Nikola Tesla. Once regarded as the archetypal mad scientist, the Austrian-born Tesla was an innovator and inventor who patented literally hundreds of groundbreaking ideas. And here, in 1895, one of his designs would be at the heart of the first large-scale generating plant in the world, a new super-efficient form of transformer.
Here you would have seen 2 rows of massive AC transformers. These stepped up the voltage from the adjacent power plant and distributed it directly from this building 25 miles down the road to Buffalo.
Tesla's transformers were the magic that made this groundbreaking power plant possible.
To demonstrate what a transformer does, we have the simple racetrack set up here. And I'm going to start by supplying the same amount of voltage to each track. just over 6.8 volts. Okay, so let's give it a try with both tracks at the same voltage. That's exactly what we expected. The dead heat. Now let's do the same experiment again, but step up one track's voltage with a transformer. So now, let's race. Sure enough, the stepped up voltage produced a faster car.
A step-up transformer works by sending power into a primary coil, which will create an alternating magnetic field. When a secondary coil that has more windings on it is placed beside it, that alternating field is transferred and, thanks to those extra windings, creates an output with a higher voltage.
And sure enough, that's reading almost 2 times what we had originally. Purple car should win. Perfect.
Instead of shooting cars down a track, Tesla's transformers enabled the power company to shoot electricity great distances across the country. A massive engineering breakthrough pioneered in this historic building, now considered to be the birthplace of the modern hydroelectric power plant.
The Niagara Falls power plant is now one of the world's largest sources of electrical power, providing up to 2.5 million kilowatts of electricity. Thanks to Tesla, the impossible was made possible.
At the Three Gorges power station, they're taking Nikola Tesla's innovative ideas and supersizing them.
This is the main transformer of the Three Gorges power plant. This is to change the voltage into a high voltage. For example, the voltage from the generator is 20 kilovolt, and this is to change the voltage into 500 kilovolt. The reason we step the power is we need a long-distance transmission. For example, we need to transmission the electricity to Shanghai. It's about 1,000 kilometers.
The Three Gorges power plant now generates almost 100 terawatt hours, supplying 9 provinces and 2 cities, including futuristic Shanghai, producing more hydroelectricity than any other facility anywhere.
Three Gorges power plant is the largest hydropower plant in the world.
When the giant ship lift becomes fully operational in 2016, it will signify the completion of one of the most remarkable engineering schemes in world history.
The Three Gorges Dam has been one of the most ambitious projects ever, taking tens of thousands of workers, 17 years to build, and costing billions of dollars. But in the end, it is truly an engineering marvel.
By learning from the great pioneers of the past, adapting, upscaling, and making innovations of their own, its workers have created a dam and hydroelectric power plant unrivaled on planet Earth. For engineer Qihua Ding, it represents the culmination of a lifetime's dedication.
It's my whole life work, and I feel very proud every day. I think the dam is amazing.
Nestled in the southern corner of the Massif Central in France is the tranquil medieval town of Millau. However, for decades, every summer, that tranquility was shattered. Lying directly in the path of the fastest and busiest transport link between Paris and the Mediterranean coast, this historic town became a traffic nightmare.
Millau is not at all adapted to the motorway traffic. When the traffic from the tourists coming back from vacation in July, the other one coming down in August, it could be necessary to have 3 hours to cross Millau.
Finding a solution would become engineer Millau Viaduct's biggest challenge. To bypass the town and unblock this vital route across Europe, he would need to achieve what was previously thought impossible: build a road across the gargantuan Tarn Valley.
The first difficult point was to select where to cross the valley, because there is almost 300 meters between the plateau and the deep part of the valley. There have been big debates at the time, many alternatives were analyzed. Finally, it was decided to fly over the valley.
To achieve this extraordinary feat, engineers created a masterpiece. The Millau Viaduct. Spanning a staggering 2.5 kilometers and towering 343 meters above ground, it is the tallest bridge on the planet. Touching the Tarn Valley floor only 7 times, the slender concrete piers support a 36,000-ton aerodynamic steel deck, held audaciously in place by a single row of 154 super-strength cable stays. Completed in 2004, this magnificent sky bridge has pushed modern architecture and engineering to its limits.
Many thought it was impossible to build that bridge, and there have been many controversy on the bridge type.
So much controversy that in 1993, an international competition was launched to find the solution. And the prize was awarded to architect Lord Norman Foster, alongside engineer Millau Viaduct.
Each new bridge is a new challenge, a new project, and must be designed very specifically. In this case, we had a very important series of problems to solve.
Not only did the bridge have to span one of Europe's deepest and widest valleys, but rest on an uneven valley floor and be subjected to extreme wind forces at deck height. But perhaps the biggest challenge of all, it had to be completed in less than 4 years and built to last.
What is very important is to give the durability to the bridge. The contract specifies that the lifetime of the bridge is 125 years, so it's something very important.
So how do you create such a colossal bridge of extreme strength in record time? Engineers first needed to choose the right materials, a task that would not have been possible without the great innovators of the past. Man's earliest building materials were sourced from nature. Neanderthals built shelters from the bones and tusks of woolly mammoths, usually when the mammoth had finished with them. For thousands of years, Mongolian nomads have used sheep wool to line the walls of their yurts. Although not everyone's happy about it. From the time of ancient civilizations, many houses have been built with straw and clay bricks. reinforced with a touch of animal dung, which works perfectly if you're standing in the right place. But to create a truly enduring structure, engineers at Millau would look to the work of a pioneering British civil engineer a quarter of a millennia earlier. Professor Luke Bisbee is taking a trip into the English Channel, one of the world's busiest shipping lanes, to find out more.
I'm heading out to the Eddystone, one of the most treacherous rocks in the English Channel. And it's a place that arguably marks one of the most important moments in civil engineering history. Today sits a 50-meter tall lighthouse designed by James Douglas in 1882. Amazingly, this is the fourth lighthouse that stood in this spot.
"22 kilometers from the busy port of Plymouth, over the centuries, the Eddystone Rock has sunk countless ships. As maritime trade increased in the 17th century, it was ordered that a beacon of light be built on top.
A building that could withstand the elements out here, the pounding of the waves day after day and the wind and the rain, requires a real engineering achievement.
In 1696, it was Henry Winstanley who completed the world's first offshore lighthouse, a 25-meter wooden tower. But 7 years later, it was obliterated by a storm. Its replacement survived 47 years, until being destroyed in a fire.
And if a lighthouse was going to last any substantial amount of time out here, a new engineering solution was needed.
In 1756, this seemingly impossible challenge fell to engineer John Smeaton. He believed that the sea must give way to the building and decided to build a lighthouse made of stone. But it was how he joined the stones together that was truly revolutionary and earned him the title the father of civil engineering.
Smeaton's original lighthouse stood on this spot for over 120 years. And in fact, we can still see the bottom half of it as that stump of a lighthouse over there.
The structure had been so strong, it was only cracks in the rocks that it sat on that forced engineers to dismantle the lighthouse and later rebuild it on Plymouth Hoe in homage to Smeaton's genius. And the secret of its success had been an innovative bonding material that could survive the constant pounding of the sea.
Smeaton experimented with mixtures of lime, clay, and iron slag to create hydraulic lime. I'm going to try to demonstrate the innovation that Smeaton accomplished at the tower. Here we have a traditional cob mortar. This is a mixture of sand and clay and straw and lime and a bit of earth. And these types of mortars were used traditionally for many hundreds and thousands of years. And the other material that I have here is Smeaton's mixture.
Smeaton's hydraulic lime is formed inside a cardboard tube before being placed in water, replicating the rigors of the sea.
And then I'm also going to do the same with the traditional earth mixture. Got both tubes now filled with the mortar. We're going to go away for about a half an hour, and then we're going to come back, and hopefully we'll see a pretty dramatic difference in terms of how they've performed. First, we're going to look at the tube that's filled with the traditional mud mortar. We're going to see exactly how much it's set. And you can see absolutely nothing. This is the one we're much more interested in. This is the one with the mortar that's based on the hydraulic lime technology that Smeaton came up with. I can immediately feel that this one is much more solid. I squeeze it, nothing happens. If I have a look inside, I can actually see this now is very, very solid. That combination of setting very quickly and setting underwater completely revolutionized civil engineering. What Smeaton had created was the precursor to Portland cement. Portland cement's the key ingredient in all modern concrete.
The strength of Smeaton's hydraulic lime allowed engineers to dovetail together nearly 1,500 blocks of granite, creating a rock-solid structure that would stand up against the forces of nature. So solid, in fact, the Victorians found it too difficult to dismantle the base when it was finally relocated to Plymouth Hoe over 100 years ago.
So here we have the original 250-year-old granite blocks reassembled here on Plymouth Hoe with mortar, much like the original mortar. Incredible that it still looks so good. And if I look really carefully, way out there on the horizon, I can just see the base of Smeaton's original tower standing next to the new tower. This was really the game changer in concrete engineering worldwide.
At the Millau Viaduct, engineers enhanced Smeaton's groundbreaking formula to create a technically sophisticated form of modern concrete, and used it on a gigantic scale, building 7 of the tallest bridge piers on Earth.
All the piers represent something like 90,000 cubic meter or more than 200,000 tons of concrete. And this is a concrete which is of a very high strength.
But for Chief Engineer Michel Villageur to hit the 4-year deadline and avoid fines of up to $30,000 per day, each pier had to be built simultaneously at 7 individual work sites. And due to their extreme height and complex shape, radical engineering techniques were called for.
From here we can see the shapes of the piers. They look very simple, but it's very far from it.
Engineers broke ground in October 2001. Across the uneven valley floor, each pier had to be a different height. The tallest, a record-breaking 245 meters. Their octagonal shape tapers gradually, splitting 90 meters below deck height to provide greater flexibility.
It was necessary that the architect worked to make nice piers, but in the same time, it was necessary to select shapes which could be erected with self-climbing forms.
Built in 4-meter stages, engineers used a state-of-the-art self-climbing frame, a hydraulic-driven system that would push a giant reinforced concrete mold upwards.
One of the big problems, of course, was to lift concrete, because this pier, this one, is 245 meter high.
Cranes were used to lift buckets of concrete, which was then poured into the concrete mold. After each pour was set, the mold was dismantled. The frame carrying the mold was then mechanically pushed by the hydraulic jacks up the piers and re-anchored in the set concrete. The mold was then reassembled, ready for the next pour. In total, each cycle took 3 days.
You can see the lines between the different lifts, concrete lifts, and also the traces of the elements where the climbing forms could be anchored to the concrete.
The piers were completed in just over 2 years, 1 month ahead of schedule.
Developing solutions to erect the 7 piers in the same time, it was a very, very, very big adventure.
But to complete the planet's tallest bridge on time, designers would again look to history's great innovators.
A vertigo-inducing 135 meters below me lies the Severn Bridge.
To create more impossible engineering. The Millau Viaduct in southwest France is an engineering wonder of the modern world.
When it was decided to place the structure to the west of Millau, then it was necessary to design a very big bridge to cross the valley.
Spanning the yawning abyss of the Tarn Valley, at 343 meters high, this supersized bridge stands taller than any other on Earth. But during its construction, its jaw-dropping height created a seemingly impossible challenge for Chief Engineer Millau Viaduct.
The great enemy of the design of the bridge is the wind. The deck is about 150 meters above the Plateau de France, and so this means that we have rather high winds.
So how do you construct a supersized bridge to cope with hurricane-force winds and turbulence on an unprecedented scale?
The solution is to reduce the wind force.
But diminishing the effects of the wind's tremendous power on the bridge deck would not have been possible without another ingenious innovation from the past. Professor Luke Bisbee is exploring one of Britain's most iconic bridges.
All right, now this is what I'm talking about. A vertigo-inducing 135 meters below me lies the Severn Bridge.
Opened in 1966 and spanning the River Severn between Ost and Chepstow, it was the first major road link between England and South Wales.
The main section of the bridge is over 1,598 meters long, which at the time made it the longest bridge in the world. I can actually see through this hole about 1,000 meters down the bridge. It's absolutely incredible.
But whilst the length of the bridge was an incredible engineering challenge in its day, it was the weather that posed the greatest problem of all. Lying inland from the Atlantic Ocean, the River Severn begins where the Bristol Channel ends. The high ground of Exmoor on the south shore and the mountains of Wales on the north create a funnel for the prevailing southwesterly winds and Atlantic storms, increasing their power.
Building a bridge that could withstand severe winds was really essential. And even on a relatively calm day, standing here underneath the bridge, you really get a sense of the wind that they were up against.
During the 1950s, pioneering British civil engineer Sir Gilbert Roberts was tasked with designing the longest windproof bridge on Earth. And the biggest challenge was the deck itself.
If you look at the shape of the deck, you can start to get a sense of what the solution was. And the most amazing thing is that the shape of this bridge deck and the solution they came up with was actually a happy mistake.
When testing the original truss lattice design in the wind tunnel, the model broke. Awaiting a replacement, engineers became inspired by other aerodynamic shapes, which led to a truly groundbreaking idea.
So what I have here is a model airplane, and you can imagine that the wing of this airplane is representing the bridge deck. So a wing has a curved surface on the top, and it has a flat surface on the bottom. And this means that air passing over the wing has to travel further across the top than on the bottom.
As air passes over the curved surface, it speeds up and loses pressure. The pressure of the air below remains high and pushes up towards the low-pressure area, creating lift.
What I'm going to attempt to show you is with this hairdryer to generate some wind, the force of the little model airplane will decrease, and that decrease will signify the lift force that we've generated on the model. So there we have our starting weight, 45 grams. Right, so there we go. The engineers here didn't want that to happen to the bridge deck.
However, if the experiment's repeated in reverse, the effect for the deck is beneficial.
What we should see is that this force should increase rather than decrease. You can actually see the downward force that's coming from the wind. And that holds everything nice and taut and safe in very strong winds.
Now the curved surface is underneath, air loses pressure as it speeds up, and the high pressure above presses down.
And of course, this is exactly the principle that the engineers used on the Severn Bridge.
Sir Gilbert Roberts and his team created an aerodynamic steel box girder deck, the first of its kind in the world. Hollow and only 3 meters deep, with a cantilevered footway on each side, the deck is able to create a wind flow which holds it firmly in place. During its history, 13 vehicles crossing the bridge have blown over, but the bridge itself stays solid.
Although this beautiful bridge has passed on the burden of heavy traffic to its younger brother just downstream, it's still managed to carry more than 300 million vehicles since it was first constructed in 1966. And thanks to Sir Gilbert Roberts and his team, it's set to do so for many more years to come.
Engineers at the Millau Viaduct have advanced Sir Gilbert's inspired aerodynamic shape and created a cutting-edge bridge deck of their own. 1 kilometre longer than the Severn Bridge, at 2.5 kilometres and weighing a colossal 36,000 tonnes. It's one of the longest cable-stayed bridge decks on Earth.
The deck is streamlined. That means that it's rather shallow. It's 4.2 meters. And in addition, it has a continuous shape, very, very limited inclination, helps the wind passing below and reduces automatically the wind forces.
The deck is a shallow trapezoid shape, creating an inverse aerofoil to provide negative lift in strong winds. But building this colossal seamless aerodynamic steel deck in record time was an unprecedented challenge. So engineers decided to create a gigantic steel jigsaw puzzle, cut in dedicated factories across France and transported to Millau.
The central core, which could be spine of the bridge, has been assembled in a segment of 20 meters and brought with trucks to the site. The deck was assembled on the hills on each side.
2 work sites on each plateau were set up to receive the component deck parts. In all, 2,000 convoys loaded with cut steel travelled to Millau. The welding was completed in just 20 months, using a staggering 150 tons of welding material. But engineers at the viaduct were yet to face their greatest challenge.
One of the big questions was to launch the bridge from both sides of the valley. And it was not so simple to do that.
To span the huge chasm of the Tarn Valley, engineers would once again turn to the work of historic innovators.
All of these harness the properties of a revolutionary product. Wow, look at that.
To make the impossible possible. The Millau Viaduct in France's Massif Central is a work of engineering virtuosity. Taller than the Eiffel Tower, this bridge once seemed an impossible dream. Conceived by engineer Michel Villager, the project pushed the boundaries of construction.
It has been very difficult. The solution was not immediate. We had to work a long time to solve the problems, and it was a big challenge.
Perhaps the biggest problem to overcome was to place the 2.5-kilometre steel deck on top of the concrete piers. Their extreme height ruled out using a crane. The only option for engineers was to try to slide the 2 sections of deck from each side of the valley.
The piers are so slender that classical launching techniques would have been very critical. It would not have been possible.
The leading edge of the deck weighs 7,000 tons. The pier's great height-to-width ratio meant that they were susceptible to lateral forces. Pushing the deck across the pier's surface would create friction, increasing the lateral force, with potentially disastrous consequences. To solve this seemingly impossible challenge, Michel and his team at Millau would need to reduce friction throughout the launch process, a task that would not be possible without the ingenious engineers of the past. Friction has been a sticking point for man for thousands of years. Heave-ho. Ancient Egyptians, struggling to slide their building blocks across sand, realized water created a smoother, slipperier surface. Woohoo! Although too much was not advisable. It's thought the builders of Stonehenge rolled their giant slabs across a series of logs, which was the perfect solution, as long as the ground was flat. Look out! But luckily for engineers at Millau, a scientific mishap made in a US laboratory during the 1930s would provide a solution. Engineer Rhys Morgan is getting to grips with this accidental discovery that revolutionized the way we live.
Most people will recognize these day-to-day objects, but what most people don't know is that all of these harness the same properties of a revolutionary product called PTFE, or to give it its full name, polytetrafluoroethylene.
This groundbreaking product was mistakenly created by an American chemist, Roy Plunkett. In 1938, whilst developing non-toxic refrigerants, an experiment with a gas, tetrafluoroethylene, went awry. It unexpectedly solidified, coating the inside of the test tube with a waxy resin. Inadvertently, Plunkett had created what would become the world-renowned trademark, Teflon.
It has lots of different properties. It's very corrosion resistant. It's chemically inert. It doesn't react with other materials. And it has a very high melting temperature. But above all of these, it's very, very slippery.
And being slippery means it's very adept at overcoming the forces of friction, a phenomenon that is hard to deal with for a standard metal.
So here I have a sled connected to a metal tray underneath and about 45 kilos of bricks and sand. And as I pull the sled along, the tray is going to have a huge amount of friction against the metal sheet here. And that friction is retarding the motion. As I start to pull against this now, you can see I've got 5 kilograms and I've still got no movement. So that's the friction preventing my sled from moving. I'm up to 7 kilograms, 10 kilograms, 11, 12, and there it goes. So that's about 120 newtons of force to pull those along.
To see how PTFE performs, the metal tray is prepared, then sprayed with the slippery coating, and cured at 430 degrees Fahrenheit.
Wow, look at that. That looks incredibly smooth. So let's give it a go. I've got 2 kilograms, 5, 6, 7, and look, it's starting to move already. 7 kilograms here to overcome the friction. And you compare that to 12 kilograms, that's 120 newtons. So that's about 50 newtons difference to move the same amount of weight.
PTFE is made solely of carbon and fluorine atoms. Fluorine has the highest electronegativity of any element, repelling all other atoms. The fluorine wraps around the carbon, so it's unable to react to anything. As a substance, it is therefore highly unreactive and creates almost zero friction. The sledge can carry up to 40% more weight when pulled across the PTFE-coated sheet, the equivalent of a 5'9" engineer.
How much are we seeing?
Wow.
There you go, 12 kilograms, 120 newtons. How about that?
Engineers at the Millau Viaduct took PTFE and incorporated it in a unique mechanism that would conquer the launching problem once and for all.
It was necessary to create a system where the launching force was created pier by pier in such a way that no force, no bending was produced in the piers.
To do this, the team created a translator, a machine that uses the slipperiness of PTFE and hydraulic jacks to lift the deck off each pier entirely before moving it forward.
At this point, we have one of the equipment which has been used to launch the bridge. On each support, we had 4 of these machines.
Each translator uses 2 wedge-shaped blocks coated in PTFE. A hydraulic ram pulls the upper wedge, which slides it up the lower wedge. This lifts the deck away from the pier, pushing it forward at the same time. The lower wedge then slides backwards, lowering the deck back onto the pier. Each cycle moves the deck 600 millimeters.
All the launching systems are moving in the same time by the same distance, and so you can understand very clearly that it's not producing any force in the piers.
But before engineers could begin the launch, there was another problem.
The typical spans are 342 meters long, but it's much too long to be crossed directly. So it was necessary to install in each span a temporary support, a big truss, in order to divide the span by 2.
7 temporary piers were built across the valley, and in February 2003, the launch began. But as the 2.5-kilometer deck was pushed out into the void, the course was not straightforward.
Here, from the north abutment, we can first see the curve of the bridge. The bridge is curved with a radius of 20 kilometers, which is very, very large.
As the 2 colossal sections progressed their curved course from opposite sides of the valley, engineers had to rely on GPS technology to ensure pinpoint accuracy. And in May 2004, 15 months after they were first launched, the 2 sections of deck finally met above the Tarn River. And incredibly, they were only out by a few millimeters.
This system was really the key of the success.
But to complete this audacious bridge, the team at Millau would once more need inspiration from the great innovators of the past.
Today, the bridge is considered a real landmark breakthrough in the world of engineering.
To create more impossible engineering. Connecting the high plateaus of France's Tarn Valley is the Millau Viaduct. This audacious road bridge is the country's tallest structure. and is one of the greatest engineering achievements of all time. Conceived by engineer Millau Viaduct and designed by architect Norman Foster, environmental considerations were key.
The first thing to do was to preserve the quality of the site because it's a beautiful site.
The unstable limestone ruled out a suspension bridge, which relies on firm anchor points at each end to take the weight of the deck. For Millau Viaduct, there was only one solution.
I wanted to design a cable-stayed bridge because cables are very strong. They allow to make very, very modern structures, very light and transparent. So it was, from the beginning, I wanted to make a cable-stayed bridge with multiple spans.
Constructing a multi-span, cable-stayed bridge on such a huge scale in a hostile environment was considered an impossible challenge. One that could not have been overcome without the ingenious engineers of the past. Structural engineer Jonathan Ledin is paddling the great Strömsvatudal in Sweden, searching for the source of an historic engineering breakthrough.
For centuries, this stretch of river here in Strömsund has been an obstacle that travelers needed to overcome.
As cars became more commonplace by the early 1950s, it was decided a suspension bridge would be built. However, German engineer Franz Dissinger, who won the commission, proposed a different idea. A key player in rebuilding Europe post-World War II, where 15,000 bridges were destroyed, Dissinger's construction solutions were cost-effective and efficient.
What Dissinger built was this, the Strömsund Bridge. A cable-stayed design that has since been recognized as a landmark in engineering history.
After carrying vehicles for over 60 years, the supporting cable stays are being replaced for the first time. And it was Dissinger's approach to installing these cable stays all those years ago that was to prove so influential. The way a cable-stayed system works is simple, yet very effective.
Imagine my arms are cantilevering out from my body like this, and I'm trying to hold the buckets of water in place like this. I need to do a lot of work with my arms. This is not exactly easy to hold on to. I'm going to use this rope here to represent the stay cables attached to the bridge deck. And I'm going to pull that over my head, which is representing the piers. So now the majority of the weight is no longer carried by my arms, but through the cables onto my head and down to the ground. And that is exactly what is going on behind us. The weight from the bridge and the loads from traffic are being transferred through the cables and down onto the piers.
Early cable-stayed bridges, however, were structurally weak. Rudimentary cables and limited understanding of the forces at play in the system meant by the early 19th century, the idea was all but abandoned.
And the problem that the engineers were struggling with in the past was designing the cables so the loads would be distributed evenly among them. The consequences of one or more cables being overtensioned could potentially be disastrous.
To overcome this problem, Dissinger looked to mathematics. He created formulas to calculate the forces required of each cable. Each of those cables was then precisely tensioned on site, and engineering first. Now they're being renewed using exactly the same process.
So these are the brand new cables that are going to be installed overnight. And just as would have happened all those years ago, they're first going to be mounted in place and then precisely tensioned. Dissinger's innovative approach makes this possible to do in just a few hours.
Dissinger's pioneering construction technique has influenced some of the most iconic bridges around the world.
So the work has been going on here on site all night. And what's remarkable is the way in which all of this is being done is really not that different from what would have taken place here all those years ago. So today, the Strömsund Bridge is considered the first true modern cable-stayed bridge and the real landmark breakthrough in the world of engineering.
Engineers at Millau have taken Dissinger's methods and magnified them, and created a structural masterpiece.
The originality of this bridge is that it is a cable-stayed bridge, but with multiple spans. This is really very special.
Whereas the Strömsund Bridge has only one central span, the Millau has 6. So as the 700-ton pylons were erected, engineers had to trust they'd calculated the perfect distribution of rigidity and flexibility throughout the structure. Key to its success lay with the cable stays themselves.
So this is one of the stay cables of this bridge, which procures the necessary resistance. In fact, for each of the 7 pylons, we have 11 stay cables on each side, so 22 per tower.
The strongest cables are made of 91 steel strands and have the breaking strength of 2,000 tons.
These cables are more resistant than ordinary steel, and this is why stay cables are extremely efficient to design very long spans.
They're so strong, engineers installed just a single axis, and only when tensioned did the entire bridge become rigid. After little more than 3 years of construction, the integrity of the bridge could now be tested. 28 trucks, weighing a total of 900 tons, were driven en masse to the center. The deck flexed, but only a few centimeters, and the bridge remained firm.
Today, I'm of course extremely proud because there are many steps in erecting a bridge like this. Finally, when the bridge was completed, it was an enormous success.
Opened in December 2004 and finished 2 months ahead of schedule. The Millau Viaduct marks a significant milestone in bridge engineering. Now used by nearly 5 million vehicles each year, for engineer Michel Villageur, it represents the achievement of a lifetime.
You know, when you have passed years working and fighting for a bridge, you know, and that suddenly it's finished, there is really a moment where you don't know what to do.
By learning from the great pioneers of the past, adapting, upscaling, and making innovations of their own, engineers and designers succeeded in making the impossible possible.
Many thought that it would be impossible to build that bridge, and now it is there.
In 2009, one of the most successful teams in NFL history needed a new home, having outgrown their old stadium. Relocating to Arlington, Texas, the Dallas Cowboys demanded an extraordinary structure.
The idea from the very beginning was really to create the finest stadium of its kind anywhere on the planet.
With such high aspirations, architect Brian Truby faced the toughest task of his career.
The engineering in the project was for us a particularly unique challenge.
But would ultimately create a structural masterpiece. The epic AT&T Stadium.
For us, when a patron enters this building, we want them to leave saying, gosh, I never have experienced anything like that.
Capable of housing 105,000 fans in a jaw-dropping 3 million cubic meters, the stadium measures almost 400 meters in length. Each end features the world's largest sliding glass doors, whilst the structure's spine is formed by the 2 longest unsupported arches in a building on the planet, holding up a state-of-the-art roof that can be opened and closed at will. This $1.2 billion stadium was conceived to be much more than a supersized football venue.
We knew from the beginning that the Dallas Cowboys would only be here 10 days a year. So we needed to make sure that this building would be alive and living for the remainder of the year.
With the Texan climate ranging from winter snowstorms to scorching summer days, designers had to control the building's environment. Their starting point, a gigantic roof.
The roof structure itself is equivalent to the weight of 99 Boeing 777s.
And they'd need to support it without interrupting the view.
One of the incredible challenges with this venue is creating that large column free space.
The huge forces that come into play to keep 104 million cubic feet column free are enormous.
So how do you hold up the largest single-span roof in the world without any supports? It's an engineering feat that would be impossible without the great innovators of the past. Since the dawn of time, engineers have struggled to hold things up. The Temple of Artemis may have been one of the 7 wonders of the ancient world, but its vast roof needed over 100 columns.
What?
To stop it caving in.
Phew.
The Romans decided to go lightweight, the Colosseum's huge ring of awnings protecting spectators. But sadly, not those centre stage.
We're on strike.
The solution for the stadium in Arlington would actually come courtesy of a construction conundrum faced during the 19th century in the Portuguese city of Porto.
In 1875, engineers were building a new rail line between Lisbon and Porto. But when they arrived here on the banks of the Douro River, their progress ground to a halt. At the time, a span of this size was considered extremely challenging, and so a bold and innovative new approach to bridge design was required.
With his specialist skills in metal structural work, French engineer Gustave Eiffel was commissioned to tackle the 160-meter void.
Now, the challenges that Eiffel faced in building his span were just immense. In addition to the width of the span, the river is also very fast flowing. It's up to 20 meters deep in flood season, and this meant that it was impossible to put piers in the water.
With no obvious way to support the bridge, Eiffel proposed an audacious solution: an enormous single arch built into the sides of the riverbank.
An arch on this scale seemed an impossible task, but Eiffel proved everyone wrong. And this is the result of his achievement. Isn't it an exquisite example of engineering? In order to make this a reality, however, Eiffel had to completely rethink arch design. Now, for bridges, the arch is actually a really brilliant shape, but it does have its limits. And I can illustrate that using this piece of card. If I place this card between two stones that represent the bridge abutments, and I place a load on it, it supports that load using compression, and the compression flows down through the arch and into the abutments. But of course, in a location like we have here, where we need a much larger span, we have to increase the length of our span, and our arch becomes much more shallow, and then the forces of tension start to take over. And as my structure is loaded, you can see that it struggles to support that load. And this was precisely the problem that Eiffel faced here at the Douro.
Solid reinforcement would simply make the arch too heavy. But Eiffel came up with an inspired alternative.
Definitely reconsidering my shoe choice for today. Bad choice of shoes today.
Luke is heading into the heart of the solution.
So here I am dangling halfway up of Eiffel's magnificent arch structure, and I have to say it's a real privilege to be able to do this.
The secret of Eiffel's success was to harness the strength of another simple shape within a network of open trusses.
And looking at the structure, you can see all the different elements of the truss, all the different parts holding the bridge up. And by making use of a simple system of triangles, Eiffel was able to create a structure that was both light and very strong and stable, and had a bigger span than ever before. And it's a real marvel of engineering. Simply genius. So to understand how this truss system works, we can make a simple comparison between two shapes that are commonly found in engineering. If we look first at the square, you can see that if I push down on it, it doesn't take long until that square deforms and collapses. And that's because the square lacks inherent stability and rigidity. But you can see if I take this triangle and I apply a vertical load to it, you can see that it's able to take that load. And that's because these two side elements go into compression, this bottom element goes into tension, and there's equilibrium created at the point where I'm applying the load.
By exploiting simple physics, Eiffel's trussed arch created engineering history by spanning the greatest distance of its age.
Eiffel's experiences here ultimately provided him with the engineering knowledge and techniques to go on to create his most famous structure, the Eiffel Tower. Not only that, but in creating this, he helped to completely redefine arch construction. And today, arches form critical parts of some of the most impressive and iconic structures all around the world.
In Texas, engineers would take Eiffel's innovation to record-breaking proportions for a building.
It's the longest continuous single arch span in the world. So we're really taking kind of inspiration from some of the bridge structures that are out there and applying it to a building.
So what you're looking at are two primary arches that span about 1,400 feet each. The size of the trusses themselves, they're about 14 feet wide, about 35 feet tall.
The stadium's twin backbones soar to almost 100 meters above the playing field. Each archbox truss weighs over 3,000 tons. creating 8.6 million kilos of thrust into each of the 4 colossal concrete abutments.
The concrete abutment then, what you see above ground, takes all those forces directly into a large concrete footing below ground. It's about 4 times larger than what you see above ground.
Each abutment required 10,000 cubic meters of concrete. Once completed in July 2007, work could begin on erecting the awe-inspiring arches.
They basically would start at the abutments on each end, and they would start with a single truss, and they would build towards the center.
Over an 8-month period, a series of 6 shoring towers were erected to support each span, before the connecting keystone piece finally fell into place. Only then can the arches take the strain and eliminate the need for even a single column to spoil the view.
Placing that keystone piece in the truss, that's really the first time after that that the structure's allowed to load on itself.
But they still faced further challenges and would have to turn to the great innovators of the past.
The difference in height between the front of this carriage and the back of this carriage is about 13 feet.
To produce more impossible engineering. In Arlington, Texas, engineers have created one of the largest sports and entertainment venues on Earth.
What you see here really is the most transparent stadium in the world. And you can see the arches, for instance, that span the entire length of the building, about a quarter mile.
For architect Brian Truby, this stadium has changed the face of arena design.
From an engineering standpoint, there's really very few structures like this.
During 2008, after 8 months of construction, the steel arches were finally in place, allowing engineers to continue with the stadium's roof.
So the roof itself actually covers about 660,000 square feet. And the reason for the shape of the roof tracks back to Texas Stadium.
As the former home of the Dallas Cowboys, Texas Stadium was renowned for its distinctive domed roof structure. Keen to keep tradition alive, the owners were also determined to retain another historic detail.
The iconic hole in the roof is very signature to us. Someone once said it's a hole in the roof so God can watch his favorite team.
But to cope with all weathers, a retractable roof sitting on top of the arched dome was the only viable option, creating a seemingly impossible problem for project engineer Guy Decker.
One of the largest challenges that we had is that arch shape of the roof structure below. It's not natural for a retractable structure to be on top of that. It creates a very steep slope, particularly when you get to the ends. At the very steepest level, we're at a 23-degree angle, which is really the steepest retractable roof that's ever been done.
So how do you maneuver a 760-ton roof panel up such a steep incline? Achieving this might not have been possible without a high-altitude innovation from over 150 years ago. Architectural historian Jen Mason-Garb has come to the White Mountain National Forest in New Hampshire to see an inspired invention many believed couldn't be built.
With an elevation of 6,288 feet above sea level, more than 1,900 meters, Mount Washington has long been the site of exploration since the late 18th century. But it's got bad weather and rough terrain and an incredibly steep grade, and so only the most adventurous climbers were able to make it to the summit to see the stunning views.
For this scenic beauty to be enjoyed by all, a solution would ultimately come from an unlikely source. During the mid-19th century, Sylvester Marsh was a successful businessman in the meatpacking industry. But it was his passion for climbing that would lead to his biggest accolade. Having been trapped on Mount Washington in a flash storm, he set about designing his dream, a railway capable of transporting tourists to the top of the mountain.
The basic problem Marsh faced, of course, is that this grade is simply too steep for a regular railway. In a typical car, the wheels would have spun without any friction, and the train would have slid right back down the mountain.
To overcome the extreme gradient, Marsh broke the mold, creating a steam-driven train that would literally grip the track.
When it opened in 1869, the Mount Washington Cog Railway was an engineering marvel of its day. It travels a total of about 3 miles, 2,700 feet at the base, and we're headed up there 6,288 feet above sea level, making it the second steepest mountain cog railway anywhere in the world.
And its secret lay in an incredibly effective system known as rack and pinion.
Here's a simple demonstration about how this rack and pinion system works. If we imagine for a moment that this plank of wood is the side of the mountain and I'm the train, I'm obviously going to try to get up the mountain, and you can see that I slide back down. However, if we apply a rack to the side of the mountain, and I'm still the train, my feet act as these pinions in the rack, and you can see that I can easily climb up the side.
On Marsh's system, the pinion is a toothed cogwheel, positioned centrally on the underside of the carriage to fully engage with a rack which lies between the track's running rails.
You can hear the pinion engaging into the rack, providing that extra connection and the friction that's needed to overcome the steep grade. And in fact, we're now on the steepest part of the track, called Jacob's Ladder. There's a whopping 37% grade here. And in fact, the difference in height between the front of this carriage and the back of this carriage is about 13 feet.
But Marsh's engineering genius didn't end there. To safeguard the train from rolling backwards, the cogwheel or pinion also engaged with a ratchet brake, meaning the cog could only move in one direction. If the train started to slide down the mountain, the ratchet would automatically drop, locking the wheel in place. This remarkably effective backup system ensured Marsh's train always reached its final destination.
Marsh's design was an engineering marvel. When it opened on July 3rd, 1869, tourists flocked to take the train and come up to the top of this mountain and enjoy this incredible vista. And in fact, Marsh's design became the blueprint for other cog mountain railways across Europe and around the world.
Engineers at the stadium in Texas have taken this inspired design from the railways to new heights. As its cutting-edge rack and pinion system guides the 760,000 kilogram retractable panels over the steeply inclined roof.
One of the challenges with a retractable roof on a domed surface is, of course, the curvature. So each of the panels, as they move then down the tracks, they travel about 100 feet vertically.
During construction in 2008, engineers would tackle this incline by mounting over 400 meters of mechanized railing onto the arch structures.
The amount of engineering that went into this was really massive. You know, you have structural, electrical, mechanization.
The 6,000 square meter panels are then made mobile with the rack and pinion system.
can see the rack here, and then the gear pin here will interlock with this. So it's an extremely robust connection that very directly connects the roof to the retractable portion.
The system is so precisely engineered, the gigantic roof needs relatively little muscle to move it.
The retractable roof is powered by a series of 7.5 horsepower motors. Each side is powered by 64, so it's roughly a Corvette engine pulling and pushing the roof as it moves along.
When closing the roof, the motors have to generate nearly 1,000 horsepower to overcome the demanding 23-degree incline. Whilst opening them creates an altogether different challenge.
There's a lot of energy generated as they move back down because of the weight of the panels themselves.
With the motors now acting as brakes, the roof reaches its final position after just 12 minutes. And when combined with the world's largest sliding glass doors, this awesome structure offers a unique experience.
When everything is open, you really have almost an outdoor experience that you would get in an outdoor venue. I think that flexibility and that uniqueness is what sets the stadium apart.
But to truly rank amongst the world's most revolutionary buildings, engineers would once again turn to the great innovators of the past.
Wow, this is incredible.
To create more impossible engineering. In Arlington, Texas, engineers have created a modern structural marvel.
This building is about 3 million square feet. The largest stadium built to date is about 2 million square feet, so we're a third larger.
Boasting a gigantic retractable roof and the world's largest glass sliding doors, the structure literally embraces the elements. But if it was to succeed as a year-round multi-event venue, the sweltering summers would demand more technology.
We really felt like our fans deserved a venue that would be able to be climate controlled, and mainly for the heat, because it gets really hot down here in Texas.
Keeping the spectators comfortable, whatever the weather, would pose a huge engineering problem.
There were two big influences, the external heat hitting the building and heating it up, and you've got 80,000 plus fans generating heat. You've got all the technology, including video and sports lights. All those things create a particular challenge.
So how do you keep such a vast stadium at the perfect temperature? To find the solution, its designers would have to look to another great innovator of the past. Man has strived to keep cool for centuries. Roman Emperor Varius Avitus demanded mountain snow be brought to his garden during the summer to make the most of the natural breezes. But unfortunately, his comfort was short-lived. In 2nd century China, it's said that inventor Ding Huan created a mechanical fan system to provide the perfect temperature for a room full of people. Except, that is, for the unfortunate operator. But it would be the early 20th century before a predicament in the print industry inspired one of the coolest inventions in history.
In 1901, a young engineer called Willis Carrier was summoned to a publishing company with a problem. Because the factory printed in colour, the paper had to go through the presses multiple times to build up those different layers of ink. But because of the heat and the humidity, the paper would swell and shrink every time it was put through, and that would mean the colours ended up not being aligned, ruining the prints.
25-year-old Willis Carrier's idea relied on a simple but very effective scientific solution. Physicist Andrew is heading into an artificial jungle to put the concept to the test.
We've come here to the tropical biome of the Eden Project in Cornwall. Now, it's not especially hot in here, it's about 25 degrees, but it's very humid, above 90%. Here we have a modern reimagining of Carrier's invention. We've got a nice big fan here on the back, and on the front we've got this spiral of copper tubing. So what we're going to do is pump some cold water through that copper tube. We're going to suck the hot, humid air from all around us in through the back of the fan. And as if it wasn't enough of a challenge taking on the jungle, we've also got this kettle back here, which, when it starts to boil, is going to produce a lot of steam. Down here, we have our reservoir of nice cold water. It's full of ice packs. And inside here, we've got the pump. So what I'm going to do is just start the pump up. And over here, just switch on the fan. And you can see this hot, steamy, humid air is being sucked through the fan.
As the water vapour in the humid air hits the cold pipes, it condenses, turning it into a liquid state.
And even though it's only been on a very short period of time, it's already sucked all this water, this humidity, out of the air.
And Willis Carrier's method to reduce humidity at the publishing company had another welcome side effect.
And on this side, it's actually quite pleasant. It's lovely, it's cool, and it's very dry.
The dry air was also at a lower temperature. The modern air conditioner was born. Factories and hospitals would be transformed by its technology, until in 1922, the advent of a centrifugal chiller allowed entire buildings and department stores to enjoy the comfort of his engineering innovation.
Today, air conditioning units are completely ubiquitous. They allow us to control ventilation, to clean air, to dehumidify, and most importantly, to control its temperature. Willis Carrier's invention truly has made the impossible possible.
Engineers at the mega stadium in Texas have taken Carrier's groundbreaking invention to a staggering scale.
What you'll see as you look across the top of the upper bowl are huge ducts. Many of these ducts are about 6 feet in diameter, so you can actually walk through the middle of them.
The system can throw out 11,000 tons of cooling capacity. But the key to keeping the spectators comfortable is directing the air's flow using the laws of physics.
What they're doing is delivering a curtain of air that washes down over the surface of the seating bowl. So we're really not air conditioning all 104 million cubic feet. We're actually air conditioning a zone about 10 to 12 feet tall.
This downward flow of air-conditioned air blanketing the spectators remains in place because of its density. As it's cold, the molecules are packed close together, increasing its weight, whilst the low-density hot air rises, accumulating in the vast space in the domed roof.
The size of the interior is one of our key physical properties that allows us to separate the cooled air from the heated air and keep the seating bowl cool.
Despite their cutting-edge climate control, to truly become a 365-day venue, engineers would face perhaps their most important challenge: to create a supersized surface to suit all needs.
We knew that it needed to be a venue that would not just house the Dallas Cowboys. We wanted to be able to be flexible so that we could move our field out to grass, or grass to concrete, or concrete to wood.
To create a super flexible surface, engineers would have to seek inspiration from a structural masterpiece from the past. Civil engineer Alfred Castillo Jr. has been given privileged access to an engineering icon that has been closed to the public since 2008.
Wow, this is incredible.
Opened in 1965, the Astrodome in Houston redefined sports architecture.
Prior to the Astrodome, stadiums here in Texas, they were built completely open to the elements, but coming to a baseball game in the middle of a Texan summer isn't exactly a great deal of fun.
Legend has it that developer Roy Hofheinz was moved to build the stadium after his young daughter complained of the heat and mosquitoes when they attended ball games together. The result was a $35 million+ stadium that could comfortably house the Houston Astros away from the glare of the Texan sun.
It was the world's largest indoor arena with a circumference of nearly half a mile. At 350,000 square feet, it made it the largest air-conditioned room on Earth.
But despite its record-breaking statistics, 60 meters above the grass playing field lurked a small but significant problem.
Players used to complain that the lucite in the dome roof would reflect light, and therefore making it virtually impossible for them to catch a fly ball. Some of the panels were painted white, but then that led to another problem. The stadium grass started turning brown and eventually died.
Having to resort to painting the mud green, the stadium needed a solution fast. Two American engineers, James Faria and Robert Wright, had the answer. The pair developed chemgrass, a new synthetic turf consisting of a carpet of nylon grass blades stretched across a thin rubber base. After its trial at a Rhode Island school, the innovative product would be rolled out at the magnificent Astrodome.
And in 1966, the Houston Astros played their first ball game on a fully artificial field that, in honor of the stadium, it was renamed to AstroTurf.
This piece of engineering genius would provide a resilient playing surface for nearly 40 years, whilst its portable nature also allowed the Astrodome to host anything from basketball to motor racing until its closure.
AstroTurf changed sports architecture around the world, and the Astrodome provided the blueprint for an indoor multi-purpose venue.
You could fit 3 Astrodomes into Arlington's mighty stadium, whilst its pioneering artificial turf has been taken to a whole new level.
You know, it's about 120,000 square feet of surface area, and it's really the stage. What you see here is the result of 30 or 40 years of technological advance and creates really the finest playing surface.
During construction in 2009, it would take 9,500 meters square of the state-of-the-art synthetic turf to cover the stadium's concrete substructure. As well as satisfying the Dallas Cowboys, it also proved to be the perfect engineering solution for a multi-event venue.
Synthetic turf really rolls up just like carpet, rolls back out, takes about 10 hours.
We have this surface for the Dallas Cowboys. We have a completely different field for college football. We've had grass in here for soccer, and we have had basketball here as well. I certainly think the multi-use aspect of it will be one of the legacies of the stadium.
But to create a venue that will truly make its mark in history, engineers would need to turn to yet another great innovation of the past.
It was here, at Wimbledon, that the BBC's first live broadcast of a sporting event would take place.
To produce more impossible engineering. Arlington's colossal billion-dollar stadium is the largest dome structure in the world.
It truly is a one-of-a-kind venue and really an incredible engineering feat.
This building has really changed the way these buildings are perceived.
Despite its record-breaking statistics, in the face of stiff competition, the stadium has had to push the boundaries even further to pull in the crowds.
For us, our biggest competition is not the team on the other side of the ball. It's network television.
You can set up one of the finest TV, surround sound, high-tech environments in your own house. So what we had to do here was be better than that.
So how do you create an unparalleled viewing experience for every fan in such a vast stadium? This huge challenge would have been impossible without one of the 20th century's greatest innovations. London's Alexandra Palace, an iconic building that was once at the centre of an engineering phenomenon.
At the beginning of the 1930s, the race was on amongst some of the world's finest minds to develop the first universal, standardised broadcast television system.
Scotsman John Logie Baird had invented a mechanical method of transmitting a moving image, whilst in the US, Philo Farnsworth had developed a rudimentary electronic version. But engineers were intent on improving their pioneering technology.
Leading the charge in the UK was a team of British scientists led by the Russian Isaac Schoenberg, hard at work here at Alexandra Palace.
Whilst the idea of broadcasting moving images into people's homes was in its early stages, engineers were building on simple technology of the very first cameras.
The basis for recording any image is capturing light. And what we've got here is a simple model of a camera. So we've got a big black box and we've got this hole in the front. Let's go around and have a look, see what we can see. Well, actually right now, not very much, because that hole is so big that all the light is bouncing off the objects in front of the camera. It's coming through that hole and it's not really ending up anywhere in particular on the screen. We've just got a wash of light. So what we need then is a lens. And as our lens, I'm going to be using this magnifying glass. So if now we pop that, there we go, on the front of the camera, I can actually bring the scene in front of the camera into focus.
The technique of recording a moving image onto film for cinema was developed in the late 1800s, but transmitting it to be viewed simultaneously in another location was a much greater challenge. An ingenious innovation created several years earlier by Russian engineer Vladimir Zworykin would, however, offer a starting point. By 1931, he patented a camera tube known as the iconoscope. Within the tube, a captured image was projected onto a mosaic of light-sensitive material, breaking it into thousands of picture elements known as pixels. A sweeping electron beam then charged the pixels before they were fed out of the camera.
Zworykin's invention allowed us to turn a picture into an electrical signal, but it was how that moving image was transmitted and then replicated on a screen at the other end that's the really incredible part.
Schoenberg's team refined Zworykin's technology, creating the Emitron, the BBC's first industry-standard camera. And by 1937, it was possible to broadcast live into people's homes.
It was here, at Wimbledon, that the BBC's first live broadcast of a sporting event would take place, with the men's final being beamed into homes across London.
And the hefty young man from across the Atlantic defeated the good-looking Continental 6-3, 6-4, 6-2.
The key to transmitting television pictures lay in how the images were extracted from the camera.
So imagine this is a single still image of a tennis champion. It's a bit hard to believe in this case, I know. What happens is that inside the camera, that image is scanned into individual lines, broken down like this. And then these lines are taken out of the camera up to the transmitter, transmitted through radio waves, which are picked up by the aerial on top of your home. Then they're brought down into your television, where these lines are reassembled again into a full image. And obviously, this has to happen very quickly. Oh, there we go. Schoenberg's Emitron camera system used 405 lines, what was then considered high definition. I'm not sure I can manage that many.
Schoenberg's 405 lines of data created one frame. To create a moving image, TV sets had to reconstruct 25 individual frames every second, fast enough for the image to appear to be moving.
And this illusion of movement is much the same as you get with a flickbook. It's by looking at a number of still images in very quick succession, you get the illusion of movement.
Transmitted through Alexandra Palace's television tower, broadcasts like the Wimbledon final would mark the arrival of one of history's greatest innovations.
It's hard to imagine the modern world without television. From transmitting breaking news around the world to covering major sporting events, TV is now central to the way we communicate and are entertained. And without it, the world would be a very different place.
In 2009, engineers at the Giant Stadium in Texas redefined the live broadcast. Installing the world's largest video board.
There's about 10.5 million LEDs. It's about 26,000 square feet of video surface. It's really unparalleled in major stadia.
It doesn't matter where your seat is, there is always an unbelievable view. You don't feel like you're in the upper deck. You feel like you are a part of the action, that you can see the passion and the inspiration on the participants' faces.
During its construction, this colossal entertainment system had to be built around a 10-story structure. Its huge scale posed an enormous challenge for engineer Guy Decker. Further complicated by its position over 50 meters above the pitch.
The structure is 72 feet tall and 160 feet wide. It's 1.3 million pounds. You know, that's a weight of 40 airplanes.
This feat of engineering is so massive, it has to be suspended from the building's backbone.
So here we are on basically level 10 of the video board. We're about 170 feet off of the ground. We have the main arch trusses, which are spanning the nearly quarter-mile span. And then we have these box trusses, which are there to provide support to the video board.
These monumental arches have once again provided a critical engineering solution to this extraordinary building.
When we were all out here and they hoisted that board up, everyone was looking at the roof wondering, did it sag? That's such a feat to marvel over and to appreciate just how complicated the engineering was.
Three, two, one.
Since opening its doors in 2009, this remarkable feat of engineering has attracted over 10 million visitors.
The first thing people do when they walk in, they go, oh wow. It's really fun to watch people's reactions.
For architect Brian Truby, it's been a life-changing experience.
Seeing the building perform is one of the most gratifying things in my career.
By learning from the great pioneers of the past, adapting, upscaling, and making innovations of their own, engineers have changed the face of stadium design.
This venue proves that if you have huge aspirational goals, you can actually attain something that's never been attained before.
And have made the seemingly impossible possible.
You know, every day I walk around and am just marveled by the feat that this building actually is.
Four, three, two, one.
For over half a century, NASA has been at the cutting edge of manned space travel. From the pioneering lunar adventures of Apollo to the epic technology of the International Space Station. Its engineers have strived to innovate. But now, NASA is undertaking a new project with the extraordinary goal of taking man to Mars.
Mars is like the holy grail of space exploration. We're going farther than we've ever gone before, into deep space, uncharted territory.
And to achieve this, engineers are having to think big as they attempt to create the most advanced spacecraft ever built.
Orion is just a huge engineering feat. There are thousands of people that are working very hard to make Orion a success.
The best engineers in the world are all working right here on this project. This isn't easy. We're going to space. If it was easy, everybody would be doing it.
The core of this revolutionary spacecraft will be the crew capsule. Measuring 5 meters in diameter, it will be the largest NASA has ever built, accommodating up to 4 astronauts. Once in space, Orion's powerhouse will be a state-of-the-art service module, equipped with unique life support and propulsion systems, and 4 winged solar arrays spanning 19 meters across, which will collect energy from the sun, allowing Orion to travel further than any exploration vehicle in history. For NASA Crew Module Manager Lara Kearney, Orion's unprecedented voyages into deep space will have an epic purpose.
I think it's important to learn about the other planets we have in our solar system, how they were formed, and whether we might be able to live there, and to be able to answer the question, ultimately, if we're alone in this world.
But the first huge hurdle facing Lara and the team at NASA is how to create enough power to even get Orion off the ground.
And when you fly a mission like that, you have to take a lot of components with you, a lot of equipment. With that crew, they're going to be gone a long time. In order to push all of that equipment a long way away, it has to be very powerful.
To make their launch a real possibility, Orion's engineers will need to look back to daring innovators of the past for inspiration. As long as man has looked up at the heavens, he's dreamt of traveling to the stars. In the 2nd century AD, an ancient Mesopotamian scribe wrote about a ship blown to the moon by a storm. But according to legend, in the 1500s, it was a Chinese astrologer, Wan Hu, who became the first person to try to reach the moon using rockets, traveling in a chair powered by gunpowder. Once the smoke cleared, he was nowhere to be seen. Whether he made it into space remains a mystery. It would take the genius of American engineer Robert H. Goddard in the early 20th century to turn the seemingly impossible dream of a rocket powerful enough to leave the Earth's atmosphere into a reality. Space historian Amy Shearer Teitel is joining the Albuquerque Rocket Society in Roswell, New Mexico, as they look to recreate one of Goddard's landmark engineering feats.
This rocket is a replica of the A-5 built by rocket pioneer Robert Goddard in 1935. And it was in this desert landscape away from populated areas that Goddard was first able to fire his rockets to really show how powerful they were.
Fascinated by space travel as a child, in 1915 he'd launched his first rocket. But the gunpowder that fueled his early prototypes was an extremely inefficient means of propulsion.
He knew that to ultimately leave the pull of the Earth's gravity, he would need a far more powerful fuel source. And so he turned to liquid propulsion, a mix of gasoline and liquid oxygen that would burn with a hotter reaction and create a more powerful rocket.
Burning gasoline and liquid oxygen together in a combustion chamber created a high-pressure, high-velocity stream of hot gas. Passing it up through two pipes and down a nozzle accelerated the flow of the gas more, producing thrust to propel the rocket upward. The higher the temperature, the greater the thrust.
And this is actually a replica of his 1926 rocket that he used as a proof of concept demonstration of the power of liquid propulsion. He named it Nell, and it flew 41 feet in just 2 seconds before it crashed.
It was a small but incredibly significant flight. Goddard had created the blueprint for all modern rockets. In 1920, he published a paper claiming his designs could be used to send payloads to the moon. Not everyone agreed. Called absurd by the New York Times, his ideas flew in the face of the accepted scientific views.
Scientists believe that because there's no air in space, there would be nothing for a rocket to push against, so it wouldn't be able to fly. But Goddard had other ideas.
Thanks to one of the most basic laws of physics, written by Sir Isaac Newton in 1686. It stated that for every action, there is an equal and opposite reaction. Unlike his contemporaries, Goddard believed this theory would apply in the vacuum of space.
So here's Newton's third law of motion in action. Imagine the skateboard is the rocket, and the medicine ball is the hot exhaust gases escaping from that rocket. As I throw it forward, the force of me throwing the medicine ball will propel me backwards with the same force in the opposite direction. So here we go. That's Newton's third law in action.
Inspired to push the boundaries, during a 15-year period, Goddard launched 34 liquid-fueled rockets, ultimately reaching altitudes as high as 2.5 kilometers and speeds approaching 1,200 kilometers an hour. And today, having been faithfully replicated, one of his engineering masterpieces, the A-5 rocket, is set to launch in the New Mexican desert.
So this is really cool. This is like going back in time. This is it. 5, 4, 3, 2, 1. That's amazing! Oh, this is really incredible. You can just imagine Robert Goddard and his team being out here doing this exact same thing 80 years ago.
Robert Goddard truly changed the face of rocket design and made the seemingly impossible possible.
He researched, developed, and understood the basic fundamental principles of modern spaceflight and developed the rockets to make it happen. Without Gotthard's contribution, human spaceflight would still be just a dream.
To launch Orion into deep space, NASA's engineers are having to take Gotthard's ingenious concept and supercharge it.
8.4 million pounds of thrust. It's taller than the Statue of Liberty, longer than a football field.
As work commences at the New Orleans Michoud Assembly Facility in 2012, Pat Whips is tasked with building the monster rocket that will first be used to send Orion on 2 test missions beyond low Earth orbit.
The Space Launch System rocket will be the most powerful rocket that's ever left the face of the Earth.
Capable of carrying a payload of 70 metric tons, 2 solid rocket boosters, the largest ever built, will generate over 75% of its thrust. The rocket's core stage, a giant fuel tank, will store cryogenic liquid hydrogen and liquid oxygen to power 4 RS-25 engines, originally designed for the Space Shuttle program.
The engineering that's gone into these engines is just incredible. I call them the Mona Lisa of mechanical engineering.
Steve Wofford heads up the team testing the Space Launch System's engines at the Stennis Rocket Facility in Mississippi.
To be able to do what they do with the efficiency that they do and harness that incredible amount of energy and produce the power that they do, it just astonishes me. I've been in love with these engines for over 25 years now.
These colossal engines are complemented by 2 gigantic 55-meter rocket boosters. In March 2015, testing begins in the Utah desert. During the 2-minute burn, engineers successfully collect data on 103 design objectives. The world's largest solid rocket motor generates a jaw-dropping 3.6 million pounds of thrust, the equivalent of 14 jumbo jets at maximum power.
These engines will get to orbital velocity of 17,500 miles per hour, which is about Mach 25.
But to eventually make its monumental journey to Mars, NASA's engineers are already devising an even more powerful version of the rocket system.
In just a few more years down the road, our 130 metric ton version of the Space Launch System will be able to take nearly 140 tons of payload, ultimately taking habitats and equipment and, of course, astronauts to the surface of Mars.
But to build a spacecraft capable of transporting man further than ever before, NASA's engineers still face major challenges and will have to draw on more innovations from the past.
They really were incredibly brave pioneers of their time.
To produce their impossible engineering. After more than half a century of space travel, NASA is undertaking its most daring project to date. Aeronautical engineers are building a new craft that will enable man to explore deep space.
Orion is going farther than humans have ever gone before.
The goal, by 2035, to land a team of astronauts on the surface of Mars.
Space is obviously a very aggressive place to be, so there are a lot of challenges.
Everything needs to work. Failure is not acceptable.
With its first manned mission scheduled for 2021, crew module manager Lara Kearney and her team have a huge problem. How to create a capsule that will ultimately have to keep its astronauts alive up to 100 million kilometers from home.
Human beings are not meant to live in space. So we have to deal with the vacuum of space, the extreme temperature conditions, the zero gravity environment, things that the human body is not used to while they're here on Earth.
Providing a safe habitat for Orion's crew would have been an impossible engineering challenge without the great innovators of history. Since the first manned launch in 1783, balloonists wanted to go higher and higher. And when, in 1899, French meteorologist Léon Tesseract de Bourg sent his weather balloons into the stratosphere, the daring aeronauts of the day were desperate to reach these dizzying heights, but soon found out their bodies simply couldn't cope. Today, Dr. Andrew Steele is treading in the footsteps of these fearless pioneers as he takes to the skies.
This is amazing. It's an incredible view. And to think that pioneering aviators would make high-altitude flights in balloons not dissimilar to this one. They rapidly discovered that the atmosphere changes dramatically as you go up. The air gets a lot colder, but it also gets a lot thinner. It gets much harder to breathe. And that's because as the pressure goes down, the oxygen molecules are more spread out, and you just can't breathe deeply or fast enough to compensate for that.
By the end of the 1920s, daring aeronauts had reached as far as 12,000 meters with the aid of oxygen. But even more extreme physiological problems were holding them back.
So what happens to your body as you go up to 12,000 meters and approach the vacuum of space? Well, I don't really want to try that myself, so I've got a little marshmallow man who's going to demonstrate it for me.
As today's flight is only hovering around 600 meters, a vacuum jar and pump are the perfect way to simulate high altitude's unforgiving low pressure conditions.
You can see now that as we're sucking the air out of the vacuum jar, the marshmallows are starting to expand, and that's because they contain little pockets of air. And as the pressure on the outside of the marshmallows fall, those little pockets of air start to expand. Now, if that was me going up to ever higher altitude, closer to that vacuum, then the pockets of gas inside my body would start to expand. And as we got to really low pressure, fluids on my exterior would start to boil. Poor guy. What I'm going to do is turn off the pump and then let the air back in. And you can see that as the pressure increases again back in that jar, it squishes him back down to his normal size. Though I don't think he's ever going to be his former self again.
Travelling higher seemed like an impossible challenge for the world's pioneering aeronauts. Until, in 1930, daring scientist Auguste Piccard proposed an audacious solution. Hidden away in the depths of the Science Museum's storage facility lies a groundbreaking craft that finally transported man safely into the stratosphere.
Piccard wanted to travel high into the atmosphere to study cosmic rays, and he didn't want to work wearing a cumbersome oxygen mask. So he knew if he was going to do this and survive, he was going to have to take the Earth's atmosphere with him. He came up with the notion of a pressurized capsule.
To get his genius design totally airtight, Piccard turned to a local beer barrel manufacturer to create his innovative two-man gondola.
The capsule is just over 2 meters in diameter, and to keep it as light as possible, it's made from aluminium just a few centimeters thick.
Once the gondola was sealed, the pilots would be kept alive for up to 10 hours by an air recycling system, evolved from submarine technology.
Once inside, the oxygen was supplied by liquid oxygen evaporating from a container, and the carbon dioxide was scrubbed from the atmosphere by a reaction with soda lime.
In 1931, a huge hydrogen-filled balloon successfully launched Piccard and his assistant to over 15,000 meters. In doing so, the two aeronauts became the first men to successfully break through to the stratosphere.
It's incredible to think what it must have been like for those two men to look out of this tiny porthole and see for the first time the curvature of the Earth stretching out beneath them. Outside it was freezing cold, it would have been impossible to breathe. They really were incredibly brave pioneers of their time.
And as Auguste Piccard safely descended to the mountains of Austria, there was no doubting that he had shaped the future of high-altitude travel.
Piccard predicted that one day we'd all fly high in the atmosphere, above bad weather and where the air resistance is lower. And without his pioneering gondola experiments, commercial air travel and spaceflight would just be a dream.
Ultimately, faced with a manned mission to Mars, Orion will be travelling 6 million times further than Piccard's pioneering two-man gondola. This epic journey will require a supersized capsule for up to 4 astronauts, creating a huge challenge for Lockheed Martin's Crew Module Senior Production Manager, Mark McCloskey.
Mass is gold, because any ounce I can save in building the structure is an ounce of an astronaut, is an ounce of something going to space.
To save weight, designers are focusing on the inner shell. Like Piccard's gondola, it's constructed of aluminium, but a super lightweight lithium alloy is allowing engineers to build NASA's largest ever capsule.
Some people will compare this crew module to Apollo. However, this is 40% larger than Apollo.
Lockheed Martin's engineers are currently assembling the project's latest pressure test vessel at the Michoud facility in New Orleans. Each of the 7 giant sections that make up the 5-meter wide structure have been machined for up to 6 months, reducing the metal's weight by up to 90%.
This is the aft bulkhead for the actual exploration mission vehicle. It's got a lot of pockets to add strength for the least amount of weight.
But to ensure the astronauts' safety, this huge capsule must become completely airtight.
This crew cabin structure has to stay together, not leak, perform flawlessly on its mission.
To achieve this, engineers are facing another historically challenging side to the construction process.
When people talk about welding, they think heat. They see a torch, they see a rod, and they see sparks. And that was welding. You know, that's fusion welding, heat.
But this time-consuming traditional technique can cause the metal to deform as it cools. So NASA's engineers have come up with an ingenious solution. Seamless joints can now be created in a matter of minutes, thanks to groundbreaking state-of-the-art machinery.
In friction stir welding, you never actually melt the metal. You get to a stage called plasticizing. So you're actually rubbing against the metal, heating it up, but never reaching the melting point, forming one solid piece of metal across.
But as well as being airtight, for the capsule to succeed, it will also have to provide a life-sustaining environment for its astronauts. To achieve this, engineers are creating the 21st century version of Piccard's air recycling system. They're currently developing NASA's largest ever state-of-the-art service module. Once mated with the crew capsule, its supersized twin liquid oxygen tanks will provide astronauts with breathable air at sea level pressure.
The life support systems include oxygen regeneration, maintaining temperature, maintaining humidity. So things you never think about on Earth because the environment takes care of it for you.
And in order to power these systems for up to 3 years in deep space, engineers are once again breaking the mold, developing 4 giant solar arrays capable of providing a staggering 11 kilowatts of power.
When you look at the combination of the crew module and the service module, you're looking at a very advanced piece of engineering, a true state-of-the-art machine.
But to create a spacecraft that can truly transport man to Mars, its designers and engineers face more major challenges and have to turn to the innovators from the past for inspiration.
It's a piece of engineering genius that's incredible for a piece of equipment that was designed in the 1700s.
To produce even more impossible engineering. The Orion spacecraft will be the most advanced exploration vehicle ever built. Designed to transport man into deep space for the first time.
Orion is ultimately the future of space flight for humankind.
And for crew module manager Lara Kearney, the project's ultimate destination is the holy grail of space travel.
Being able to get the crews to Mars will be an important part of being able to answer whether there either was or is life on Mars.
But at over 100 million kilometers away, one of the biggest problems facing engineers and astronauts is making sure they can locate the awe-inspiring planet.
Unfortunately, it is very easy to get lost in space. The task of navigating to Mars gets progressively harder the further away you go.
We only have so much fuel on board. If we get a little off target and we don't have the fuel to get back, that obviously could mean a loss of our crew.
And with the stakes so high, in order to navigate safely through deep space, the team at NASA need to call on another genius innovation from the pioneers of the past. For the ancient mariners, the vast oceans offered a similarly enormous navigational challenge. Most kept land in sight, but in the 9th century, a Viking explorer ventured further afield with a cage of ravens. On releasing a bird, if it took off in a clear direction, he knew it was headed toward land. For centuries, Mediterranean sailors were guided by the direction of the wind, confident they could recognize a chilly northerly or a sweltering southerly. But they found a still day would leave them all at sea. Fortunately, a more effective navigation solution was on the horizon. Physicist Andrew Steele is heading out to sea to investigate.
With no accurate means of navigation, early voyages across our vast oceans were either for the very brave or the very foolhardy. Once you'd lost sight of land, it was very hard to know exactly where you were.
Although mariners could estimate the direction they were travelling in from the sun's position in the sky, pinpointing their position was impossible.
In order to know precisely where you are, you need to know your line of latitude and also your line of longitude. That's this grid of lines that covers the whole surface of the globe. And it wasn't until the 18th century that instruments were developed which allowed us to do this precisely.
In 1757, famed mathematical instrument maker John Bird created an innovative device that would change the face of navigation.
This is a modern version of Bird's device. It's called a sextant. It works by allowing the user to measure the angle between different objects in the sky and the horizon, things like planets, the moon, the sun, and the stars. The sextant enabled seafarers to determine their location anywhere on the globe at any time of day or night to an accuracy of just a few hundred meters.
To see just how effective it is in today's world, Andrew will be testing Bird's ingenious device against modern GPS.
To work out our latitude, I'm taking what's called a noon sight. You look through this little telescope here at this thing, which is called the horizon glass. It's half glass and half mirrored, and that means you can look straight through the transparent half and look at the horizon. Then this mirror works in conjunction with this second mirror to reflect the light of the sun into the viewfinder. Now, by changing the angle of this second mirror, we can then bring the sun down onto the horizon. And when we've done that, we can take a reading off this scale.
But to get an accurate idea of position, mariners still needed more information. And this was first provided by the Royal Greenwich Observatory Nautical Almanac in 1767. Sailors could simply combine their own calculations on board ship with those recorded from the world-renowned observatory.
By comparing the position of the sun at local noon to the position of the sun in Greenwich on the same day, using a guide like this almanac, we can determine our line of longitude.
Providing both latitude and longitude, these ingenious innovations have enabled seafarers to plot an accurate course for centuries. But how will this historic navigational technique stand up against modern technology?
So I've taken that noon sight with the sextant, I've done the calculations, and it looks like our latitude is about 49 degrees and 55 minutes. Our longitude is 5 degrees and 27 minutes, and all that comes out to within less than 500 meters of the reading we get on the GPS.
John Bird truly made the impossible possible.
The sextant is a piece of engineering genius that has remained almost unchanged since John Bird's day. In fact, merchant ships in the Navy still carry sextants as their means of navigation. That is incredible for a piece of equipment that was designed in the 1700s.
As Orion focuses on its first test flight in 2014, it will have a host of new technology to call on as it navigates through space.
First of all, of course, we have the Deep Space Radio Network, which is ground-based tracking equipment from Earth dishes that uses the information carried in a radio signal to actually navigate the spacecraft.
But in future missions, as the capsule heads further away from Earth on its 9-month journey to Mars, like their nautical predecessors, its crew will increasingly have to look to the stars.
NASA has a very good understanding of stars and their relationship to one another. There's been a lot of mapping of the universe to understand where the stars and the planets are.
As radio signals weaken, the astronauts will need to turn to astronavigation, taking their own measurements to establish their position in deep space.
The further out you get from Earth, the more diligent you have to be of milking every piece of information.
Faced with this huge challenge, Greg Holt and his team are currently testing an innovative onboard system in NASA's state-of-the-art optical tunnel.
So this is the Orion optical navigation camera system, and the camera is actually looking at a simulated image of the moon that's not unlike the image that it would be taking in space. We're going to run that through the image processing routines on board to actually extract measurements.
This sophisticated equipment will calculate critical dimensions such as the diameter of the moon and the angle of separation between the moon and the stars, allowing astronauts to plot their location to a matter of meters.
It's the newest way to determine where your spacecraft's position and velocity is in space.
But as engineers continue to develop their mind-boggling technology, there are real concerns that the high levels of radiation in Mars's hostile environment could affect Orion's onboard computer systems.
If that were to happen at a critical time with a crew on board, it could be a very bad day.
So, as with many pioneers from the past, NASA's astronauts will turn to John Bird's ingenious 18th century navigational invention.
For the first few flights, we'll also have them carry along a sextant. They can take these measurements between the moon and the stars, good enough to get them back home safely. The idea that we're still able to use a sextant is really astounding. You can feel the salt air as you're in the spacecraft and hear the ghosts of the mariners past whispering to you, giving you advice on how to take a good sight.
But the navigational challenges facing engineers don't end there. Orion's 100 million kilometer voyage to Mars is so immense, it will have to be done in a series of gigantic space hops.
Once we're out of Earth orbit, we're going to have to dock to a habitat if we're going to stay out there for any period of time. Well, you have to be able to get into other vehicles or get out of that vehicle when you get there.
And with multiple dockings to support vehicles and even asteroids predicted, it's Frank Moore's job to create NASA's first ever automated docking system.
We can actually get the crew to a habitat without them flying it themselves.
Current tests at Lockheed Martin's Space Operations Simulation Center are replicating these complex maneuvers that would normally take up to 5 astronauts to perform.
So what we're doing now is simulating the motion of a final approach to a destination to see if the navigation system can actually correct the vehicle motion.
In space, both the capsule and the destination it is docking with will be traveling at immense speeds. So the critical approach will be achieved by a series of laser-guided sensors.
The closing velocity has to be very slow, typically about 1/10 of a foot per second. But we're traveling at 17,000 miles an hour. We have to be within a couple centimeters of accuracy. You don't want to come in too hard because you can then damage the docking port. There's no spares. They don't grow on trees.
But Orion will face an even bigger challenge on its astonishing missions. To safely return home, designers will have to look to yet another ingenious innovator from the past.
Yes! That's massively increased our surface area, and we decelerated phenomenally.
To create yet more impossible engineering. Engineers around the world are joining forces with NASA to develop a groundbreaking space exploration vehicle.
The name Orion will be up there in the annals of history with Mercury, Gemini, Apollo.
Ultimately, in 2035, the audacious project hopes to achieve the seemingly impossible goal of taking man to Mars.
Orion will usher in a completely new era of space exploration, being able to take crews farther than we have ever been before and bringing them home safely.
But crew module manager Lara Kearney is well aware that the final leg of the deep space mission will be perhaps the most challenging.
This will be the first time we have ever brought anything back from the surface of Mars, particularly something as big as the Orion spacecraft.
As it enters Earth's atmosphere, Orion will be traveling 35 times faster than a speeding bullet. Its state-of-the-art heat shield protecting the crew from temperatures hotter than molten lava. But once the fierce heat of re-entry is negotiated, engineers face one more huge problem.
We're still going very fast, thousands of miles an hour, so it's a very big challenge to be able to slow down a 20,000-pound vehicle all the way down to 20 miles an hour.
This seemingly impossible task is down to Parachute Assembly's chief engineer, Koki Machin.
It's very difficult to make measurements on something that's deployed at 100 miles an hour. That has a lot to do with why they're considered the least reliable piece of the spacecraft.
Despite Orion's ultra-high-tech mission, to complete the final stage of its flight, engineers must rely on the simplest form of engineering. The fascination with defying gravity really took off in the early 1900s. The first freefall jump in 1919 transformed parachuting into a sporting spectacle, allowing early parachutists to discover new techniques. But it was the need to drop cargo and deploy troops during the First and Second World Wars that would ultimately drive engineers to push the boundaries of this vital piece of life-saving equipment. To experience firsthand the forces involved in returning to Earth safely, physicist Andrew Steele is 4,500 meters above the British countryside.
When we jump out of the aircraft, there'll be two forces acting on me and George. Gravity pulling us down, and air resistance pushing us up. And the air resistance gets larger the faster we go. So eventually we'll be going so fast, the force of air resistance will balance the gravity pushing us down, and that means we'll have reached what's called terminal velocity.
For an average man or woman, this constant speed levels out at around 200 kilometers per hour after 15 seconds of freefall.
Here we go! We've just gone below 1,500 meters. We pulled the cord and the drogue chute, which is stabilizing us during the free fall, has pulled the main parachute out of the bag. That's massively increased our surface area, and that means we've got much more air resistance than before, so we've decelerated phenomenally.
But if you want to slow down a much larger, faster moving object, a solid canopy like this will be ripped to shreds. This was a problem first faced by the Luftwaffe's engineers during the 1930s, as they struggled to control the landing speed of their newly developed jet aircraft. The solution was down to the genius of a young German engineer, Theo Nack. His innovative ribbon parachute would revolutionize high-speed air travel. Its ring-shaped canopy was broken into a series of vented ribbons, allowing enough drag to slow the aircraft down, but leaking enough air to reduce the stresses on the canopy. Aircraft could now land on shorter runways, decelerating from higher speeds faster and safer than ever before. Heralding a new era in man's fascination with air travel that lasts to this day.
Whoa. That is an incredible piece of engineering. It's revolutionized aviation and saved countless lives. Oh man, it's good fun too.
Nearly 80 years after its invention, NASA's Orion project will still rely on the historic ribbon parachute design. But as the largest capsule NASA has ever built returns to Earth, Theo Nack's ingenious invention will need to be supersized.
This parachute is the final phase of landing. This is one of a cluster of 3 parachutes.
These colossal mains each measure 35 meters in diameter, making up just one part of a state-of-the-art staggered parachute system. But equally impressive is the engineers' solution to testing. In July 2012, they embarked on their first low-velocity airdrop.
The proper test would be a spacecraft, rather expensive. So what we've been able to do is integrate our parachutes into something that looks exactly like the spacecraft and then practice deploying.
A total of 11 chutes will be needed to gradually slow the capsule down from a speed of around 560 kilometers per hour. The 7-meter drogue chute's simplified ribbon design stabilizes the craft, reducing Orion's velocity down to 160 kilometers per hour, before the pilot chutes pull out, deploying the 3 colossal mains.
When you look at a main, you can look at the fabric in here, and if you go calculate the surface area of this parachute, it is roughly 12,600 square feet. So think about your house or your apartment. How many of those would fit in one of these is impressive.
Thanks to the ingenious design of these gigantic chutes, Orion's speed will be cut to 1,000th of its outer space velocity in a matter of minutes.
By the time we get to the water, we're in steady state descent. When we hit the water, we're traveling roughly 20 miles an hour.
But despite its incredibly controlled landing, Orion's designers are leaving nothing to chance. January 2012 marks the latest in a series of tests at NASA's Hydro Impact Basin in Virginia, as engineers carry out extensive water drops, simulating potential splashdown scenarios in the Pacific Ocean. A variety of entry angles, wave heights, and wind directions are taken into account to ensure the self-righting capsule will not be tripped up in the final moment of its historic voyage.
We are committed to 100% mission success. That means the crew is always safe, and we get everybody back home safe.
Finally, after years of development and testing by thousands of engineers, December 2014 marks Project Orion's first major milestone.
5, 4, 3, 2, 1. And liftoff. A new era of American space exploration.
As it embarks on its first unmanned test flight, the state-of-the-art spacecraft soars to over 5,500 kilometers.
We're back in space business now.
Oh, yeah.
During its 4.5-hour mission, the capsule faces a variety of hostile environments. As it passes through Van Allen's belt, it's exposed to prolonged periods of radiation before being subjected to temperatures in excess of 4,000 degrees Fahrenheit. But despite these incredible stresses, critical data confirms that Orion's maiden voyage into Earth's orbit is a resounding success.
The Orion spacecraft and all of the thousands of people that are working on it are making what we thought was once impossible a possible dream.
But to make its mark in history, Orion's designers now have their sights set on taking man into deep space.
This is a tough task. We're up to it.
I think once we finally do it, we could look back and say, this is the greatest thing we've achieved.
By drawing on the innovations of the past, adapting them, improving them, and making their own discoveries, these groundbreaking engineers are determined to one day make the seemingly impossible possible.
Standing on another world, you can almost not wrap your head around that.
Awesome!
I have no doubt that Orion will be that next great leap for mankind.
Flash down right now.
13922.
In 2009, history was made with the launch of the largest class of passenger ships on the planet. Royal Caribbean's Oasis-class cruise ships take maritime engineering to an unprecedented level. Now, in a shipyard in France, a third Oasis-class vessel is under construction, and when complete, will be the biggest of the group. Longer, wider, and heavier than any passenger ship that has come before. For the project's director, Petteri Kaiso, it's an almighty engineering challenge.
The amount of technology, engineering and design that has been put into this ship class is quite extraordinary. It's simply mind-boggling. Nothing like the Oasis class of ships has been built before. This is in a class of its own. The complexity of it is really staggering.
And for Timo Ijuri-Javori, one of 2,500 people working on the new ship, the scale never fails to amaze.
Sitting next to her makes me feel like standing next to a skyscraper.
When complete, Harmony of the Seas will be almost 8 times longer than the Statue of Liberty is high, taller than 14 double-decker buses, and twice as heavy as the world's largest aircraft carrier.
She's about 360 meters long. The funnel is reaching a height of 65 meters from the water level, and her gross tonnage is 227,000 tons. She is the largest ship ever built.
Construction on such an immense scale would be impossible without a pioneering innovator from the past. The art of staying afloat has fascinated man for thousands of years.
Thank you.
The ancient Egyptians built vessels from reeds, perfect for cruising the Nile.
Oh, I don't know.
But their absorbent nature meant they weren't built to last. For centuries, wood was the material of choice.
Onward!
But warfare led to the use of metals and the mighty ironclads.
Fire!
Although iron could be brittle and prone to rust.
Oh dear.
And as mariners strived to build bigger, they needed a stronger and more resilient solution. The answer would lie in a material that revolutionized the modern world.
In the chamber behind me, there's about 150 tons of liquid molten steel. The temperature is phenomenal. It's about 1650 degrees Celsius.
Engineer Rhys Morgan is in the north of England, in the extreme environment of a state-of-the-art steel plant in Sheffield.
This is absolutely amazing. It's the best thing I've ever seen.
Different grades of steel are made by alloying iron with various metals and elements.
Oh my God! The crucial starting point of the steel-making process is to remove the carbon and the other impurities. And now it's being poured into the ladle, and it'll go to the next stage, which is to take it to the converter.
During this second process, the steel is further modified by adding extra alloys and blowing in oxygen.
What's going on here is the very basics of steel making. And this wouldn't have been possible today without the pioneering work of one engineer that's known throughout the world by all material scientists.
In the mid-1800s, British inventor Henry Bessemer revolutionized what had been for centuries an incredibly specialized and lengthy process.
Traditionally, the wrought iron was layered with charcoal and heated over days, and the charcoal would diffuse into the iron, and that would produce the steel qualities. Very complex and difficult to achieve, and therefore very expensive historically.
But Bessemer had a solution that would make steel a viable proposition for mass production.
And this is it, the Bessemer converter. It's a huge, vast, cylindrical chamber, about 6 meters high, and it would have held 25 tons of steel.
The converter's capacity may be impressive, but the contraption's real ingenuity was the speed at which it could create steel. Bessemer discovered that pumping air into the iron accelerated combustion, increasing carbon reduction and burning off impurities quicker, resulting in quality steel in a fraction of the time.
To show how oxygen injection really increases the combustion process, I've got a simple demonstration here. I've got a tray of charcoal. With my thermal camera, I can see the temperature of these coals at the moment. It's around about 450 degrees C. So now what I'm going to do is start to blow pure oxygen onto these coals and see the effect. Wow, look at that. The impact is amazingly impressive. So if I now look at the temperature, it's gone up to 1,000 degrees C, a hugely dramatic increase in the temperature of these coals. So Bessemer had found a really amazing process to reduce the carbon in steel.
As mass production took off, steel's elasticity and strength proved the perfect match for the railways and the world of shipping. At the height of its demand, 10,000 tons of Bessemer steel was produced each week in Sheffield alone.
And although processes have become more sophisticated and complex, it was thanks to the engineering genius of Sir Henry Bessemer and his revolutionary machine that over 1.5 billion tons of steel are now produced annually right across the globe.
Measuring 362 meters long and weighing 227,000 tons, the Harmony of the Seas needs a very special method of construction and assembly.
Harmony of the Seas requires approximately 50,000 tons of steel.
And the shipyard have a production line of Goliath proportions to process it. Vast steel sheets are brought into the plant by rail. There, automated systems cut the sheets into thousands of individual components.
Here we have one of the pieces. This is normal strength steel, a very typical piece. Thousands and thousands of pieces like this on board.
The steel panels, girders and smaller components are then welded into modular sections called blocks.
After the panels have been fitted with stiffeners, we start erecting the bulkheads onto the panel. And at this stage we start calling it actually a block. This is typically a 1 deck high block of steel which has the deck, the bulkheads, the pillars, everything it needs to form one deck of the ship. The block, as you can see now, it's turned upside down. So actually we're looking at the ceiling of any given deck. And the reason why it's like this is of course that it's much easier to weld everything when it's in this position instead of welding in the ceiling. And once the outfitting is mostly completed, then it's turned upside down, or the right way actually, and then you start building blocks on top of that.
The individual sections are then joined together to form what are called grand blocks, 90 in total.
Here we have one of the grand blocks, one of the 90 grand blocks. And this is actually consisting of 5 decks. It's one of the highest grand blocks we have. So for this you need probably around 10 blocks to make this one big grand block.
A custom-built, super strong gantry crane then lifts each grand block into the dry dock.
A grand block, when the crane lifted it up, it can weigh up to 1,100, 1,200 tons. And that is of course quite a massive load.
All 90 blocks are assembled to form the record-breaking ships.
It actually could be compared, and this is of course simplifying it a lot, but you can compare it to building a Lego structure actually.
But the Oasis-class cruise ships are no toy, and its designers and engineers will have to push the boundaries, drawing on the great pioneers of the past.
You can feel the vibration, and then you see slowly movement.
To create this record-breaking fleet of impossible engineering. A team of nautical designers and engineers have set themselves an extraordinary challenge: to build a fleet of cruise ships larger than anything ever seen before. The Oasis class of ships dwarfs its predecessors. And in a shipyard in France, the third of the group is almost complete. When launched, the Harmony of the Seas will become the biggest passenger ship of all time.
You can definitely call this ship a small city. It can house almost 9,000 passengers and crew on board. It's a fully self-sufficient island, if you will.
But these ships' dozens of restaurants, theatres, bars and attractions would all be impossible without one vital component, buried deep within their interior.
The engines are the heart of the ship, and the electrical network is the veins to provide the power forward to the ship. Without the engine, the ship is not alive.
So how do you create an engine powerful enough to move a floating city across the oceans and provide enough electrical juice to keep more than 6,000 passengers and over 2,000 crew comfortable and entertained? It's a problem that would have been unachievable without one of history's great innovators. The Industrial Revolution gave birth to the steam-powered engine. Although it increased productivity, it came with a very big problem. To get rid of their bulbous boilers, engineers broke the mold, burning fuel within a new engine. Compressing gasoline and air and igniting it with a spark plug to drive the piston. The internal combustion engine was an industrial game changer. But as the 19th century drew to a close, another innovation was just around the corner. Mechanical engineer Henrik Birgeau has come to Copenhagen in Denmark, a capital city which owes a debt of gratitude to a piece of engineering genius. Inspired by a truly remarkable innovator, Rudolf Diesel.
This is the Oasis power station in Copenhagen. And inside, you'll find a giant version of Mr. Diesel's early engine concept, which changed the face of the industry globally.
As it powered up in 1933, the diesel-powered HC Ørsted was the largest engine of its kind, measuring an impressive 12 meters in height and weighing 1,400 tons. Still in working condition, in its heyday, it produced a mind-blowing 15 megawatts of power.
It's absolutely huge. Standing next to this 3-4-story tall engine is very impressive.
But despite its supersized stature, the real power from this engineering colossus is drawn from Rudolf Diesel's brilliant design, patented in 1894.
It's very hard to believe that the inspiration to this piece of engineering came from an object which actually fits into the palm of your hand.
Although the internal combustion engine had made a huge global impact, Rudolf Diesel's design innovation made it even more efficient. Crucially, it didn't require a spark plug, using only compression to ignite the fuel thanks to its innovative double-acting piston.
This is a fire piston, and this little piece of kit was what inspired Rudolf Diesel in his development of the diesel engine. And it works like this. You have a small cylinder where you add a bit of cotton wool. The cotton wool will work as fuel. You have a little piston. When you push down the piston here, the air will be compressed. The temperature will increase and it will finally ignite the cotton wool. And it goes something like this. Compressing the air created heat. The heat forced the cotton wool to burn, turning it into energy, which forced the piston back up again.
The perpetual motion within the compression ignition engine worked in almost exactly the same way. Air is drawn into the piston and rapidly compressed, creating heat. Named after its inventor, high-energy diesel fuel is then added, causing combustion, which pushes the piston out to start the process once more. Unlike the spark ignition engines, it was the continual firing of this diesel fuel piston that created superior power and efficiency.
This means that you're able to burn not only many different fuels, but also cheaper fuels compared to a spark plug engine concept.
When this ingenious piece of engineering was supersized, it created the awe-inspiring HC Ørsted engine, which incredibly can still come to life more than 80 years after it was first fired up.
We're now about to ask Otto to start up the engine which was once the largest one in the world.
You can feel the vibration, and then you see slowly movement. Very, very impressive.
The 8 giant cylinders would throw out more than 22,000 horsepower, operating at around 75% efficiency, compared to as little as 10% achieved by steam engines.
Basically, what you see here haven't changed dramatically in almost 100 years.
Diesel's innovation was so remarkable, it transformed the industrial world. But its superior power and fuel efficiency had also made a huge impact in the world of shipping. The launch of the first diesel-powered liner in 1912 would transform the maritime world. Cleaner and more compact than its steam-driven predecessor, its engine was also up to 3 times more efficient, increasing range and opening up a new raft of trade and travel possibilities.
I would say within mechanical engineering, it's the most important leap, no doubt of that.
The HC Orsted in Denmark might be a monster, but the power of each Oasis-class ship is 6 times greater. The huge vessels use 6 Wärtsilä diesel engines, the largest of which is almost 13 meters long and weighing well over 200 tons. Fitting them is an engineering feat in its own right. Now, 2 years into this trailblazing project, what was once an impossible dream is finally becoming a reality for engineer Timo Ijuri-Javori.
We are now on the main engine room of the ship, and we are going to test diesel number 1. So this baby here. This is one of the most exciting days of the project. Yo, Ivo, let's start her up.
The giant engines generate electricity that not only powers the motors that drives the 227,000-ton ship across the world's oceans, but also provides enough energy for the floating city above.
It feels great to see the engine alive. In total we have 6 engines, and the total output of the ship is 93 megawatts. That equals to a power of 1,200 road cars.
Without this mighty powerhouse, the world's largest cruise liners would be an impossible dream.
Starting of the main engine is one of the main milestones on the shipbuilding project.
But to complete this structural masterpiece, engineers face more challenges and will have to turn to another of history's great innovations.
The paddle wheel's got quite a good acceleration straight from the start.
To produce more impossible engineering. In a shipyard in France, the third of the largest class of cruise ships ever built is nearing completion. When launched, the Harmony of the Seas will be a record breaker in its own right.
It is 361 meters long, 47 meters wide on the waterline. We have over 2,700 passenger staterooms, and we can have almost 9,000 people on board at any given time. Largest cruise ship in the world, pretty impressive.
The enormous scale and width of the vessels has allowed them to do something never before attempted on cruise ships. The Oasis class has a split superstructure, which allows open space through the middle of the ships.
Now we are on deck 8, forward, facing backwards. We are on the Central Park area, one of my favorite places of the whole ship. The inside cabins are not anymore inside cabins, but we have a perfect view to the park. We will have solid pavement here, live planters, just like a normal park. This concept is totally unique. You cannot find it anywhere else. Only an Oasis class has this split superstructure.
Its upper structure may be impressive, But for the ship to be a viable design, it will also have to deliver beneath the waves.
So there are a few factors that are very important for the fuel efficiency of the ship. And clearly the biggest one is the hull shape. The hull shape needs to be extremely well designed so that you have a good hydrodynamic shape.
So how do you engineer a streamlined shape to efficiently power this gigantic ship through the world's oceans? Achieving this may not have been possible without an innovative breakthrough from over 150 years ago. Dr. Andrew Steele is in the British seaside town of Torquay, a top venue for one of the most extreme forms of nautical competition.
This is a Phantom 19 offshore circuit racing class powerboat, and it's built for one thing: speed. The shape of the hull has been precisely matched to the power of the engine. And that means that this thing can cut through the water at incredible speeds, in excess of 100 kilometers an hour. This really is incredibly exciting. The ability of this boat to cut through the water would not be possible without the pioneering work of one man here in the seaside town of Torquay.
Over 200 years ago, the advent of engines transformed the maritime world. But naval designers still needed a greater understanding of how their ships moved through the water, so they could install enough power.
For centuries, shipbuilders had a kind of one-size-fits-all notion about ship hulls. There was one generic shape that was considered the most efficient, but there was no real way of testing this, of working out how much drag, how much resistance a hull would encounter as it moved through the water.
In 1870, engineer William Froude tackled this problem, building a groundbreaking facility that would set the benchmark for hydrodynamic testing to this day.
It was here at his home in Torquay that Froude built the world's first tow tank.
The 76-metre-long water tank allowed Froude to carry out precise tests at consistent speeds. Handcrafted models were mounted on a carriage and dragged through the water on a steam-driven pulley, enabling Froude to make his hydrodynamic calculations.
Froude's original tank out there in the garden is sadly no longer in existence, but we do have this lovely swimming pool. And here we're going to try to explain Froude's revolutionary discovery and how it changed the world of shipping forever. We've got three different shaped hulls: a flat-faced square box, a slightly streamlined rubber duck, and then this sleek speedboat.
After ensuring they are equally weighted, each object is towed by a rope attached to a scale, measuring the amount of hydrodynamic drag.
You can see this isn't slicing through the water, it's sort of making a load of turbulence. If you look at the scales, 3, maybe even 4 kilos. That's a lot of drag, a lot of resistance.
Next up, the slightly more streamlined rubber duck.
Well, that feels much lighter, and the scales bear that out. Maybe 1.5, 2 kilos of force there. And you can see the pool much less disturbed. There are far fewer of those eddies. The duck's just skimming across the top of the water. But I still think we can do better. Let's try the powerboat. And this is almost effortless, maybe 600 or 700 grams tops. You can see much less disturbance to the water. The pool's almost still. And even from this scale model, you can see why we make boats in this streamlined shape.
Although Froude appreciated the importance of friction between hull and water, his real breakthrough was understanding the drag illustrated by the model's wake pattern.
Froude's real eureka moment was when he realized that he could use a law to relate the drag on a scale model of a boat to one that was full size.
His ingenious formula created what has become known as the Froude number.
That Froude number can then be used to compare a model ship to a full-size one. By making sure they've got the same Froude number, you can work out how much drag the larger ship will experience, work out how big an engine you need to install, and it was this discovery that revolutionized hydrodynamics and the shipbuilding industry.
During the 1870s, Froude's groundbreaking innovation was home to over 46,000 experiments. His pioneering work paved the way for hundreds of state-of-the-art tanks in existence today, many of which have been christened with water from Froude's original tank. Engineers of the Oasis-class ships used huge 10-meter-long models in a tow tank that simulated a variety of sea and weather conditions. The result? A super-efficient bulbous bow design that has been further enhanced by a cutting-edge system known as air lubrication.
The air lubrication technology requires microbubbles, so we push the air through the bottom of the ship through a specifically designed grid that creates the microbubbles. We have them in a few locations on the ship in the forward part, and as the ship moves forward, the cushion of air moves along the ship's hull.
The velocity and size of these microbubbles orientates the airstream along the underside of the vessel. The resulting cushioning effect significantly reduces friction and the power needed to propel the ship, increasing energy efficiency by around 5%. This colossal class of cruise ship may be streamlined under the surface, but above water, their sheer stature poses a huge challenge.
As we have such a big wind profile on the ship, it's almost like driving a skyscraper at the seas. We have to be able to control her to the direct position what we want to have to be.
So how do you provide enough power, control and efficiency to maneuver such a huge vessel so it can cope with weather conditions and cruise long distances? The solution to this seemingly impossible conundrum came about over 180 years ago. Naval architect Lucy Collins is in Dartmouth on the English coast, on board a boat equipped with an innovation that dominated shipping in the 19th century.
And this is it, the paddle wheel. Once the steam engine came along, the paddle steamer was born, and it was unrivaled as the main form of ship propulsion across rivers and the seas.
During the early 1800s, paddle-driven ships such as the SS Savannah could cross the Atlantic. But as impressive as the technology was, it wasn't efficient.
So the paddles are on the side of the ship, and as it goes over waves, and particularly in rough weather, the paddles are going to start coming out of the water on either side, and this is going to reduce efficiency and speed.
Paddle steamers had dominated the seas for decades, but engineers were now looking for a viable alternative. Their inspiration came from an ancient invention.
For most of those early innovators, the focus of their attention was this, the Archimedes screw.
Dating back to the 3rd century BC, this crank-operated contraption was traditionally used to transfer low-lying water into irrigation ditches.
So we can see if we turn the drill on, we start to get water transferring up the pipe and then overspilling at the end of the pipe. So inventors realised that they could apply this to a ship. If you put the screw surface on the ship, it can push the ship through the water.
In 1836, engineer Francis Smith patented a revolving screw to power a 6-ton motor launch. But having snapped the metre-long section during testing, he realised that the remaining fragment drastically increased the boat's speed. What he had happened upon was a precursor to the modern-day propeller. Despite his discovery, the Navy was convinced that paddle power was still the future.
Adamant about the advantages of his design, Smith decided he needed to prove his doubters wrong.
he decided to pit his screw-driven SS Rattler ship against the paddle-driven SS Electro in a tug-of-war and a race.
With both ships equally weighted and equipped with identical engines, Smith's lifelong work was on the line. Today, Lucy is recreating this famous event, taking on a propeller-powered bike in her own paddle-powered vessel.
So the paddle wheel's got quite a good acceleration straight from the start. But it seems like the propeller blade is just reaching its full efficiency. And unfortunately, the paddle wheel just can't keep up. The paddle wheels are slipping, and it seems like the race is lost.
As Smith's screw-driven vessel blew its paddle-powered opposition out of the water, a new chapter in propulsion had begun.
That was the start of the propeller being the primary means of propulsion for ships, from then until now, almost 180 years later.
In order to drive the largest cruise ships in the world through the water, the propellers on the Oasis-class vessels are on a predictably grand scale. Each of the 3 bronze screws is 6 meters wide and weighs 40 tons. But creating a 21st century megaship also requires new challenges that need cutting-edge propulsion solutions.
The ports we sail into are sometimes fairly small, so we want to be sure that we can always maneuver the ship in a very safe way. So we're not dependent on tugs. We can independently maneuver the ship into the ports we want to sail into. We have to really park it on a dime.
The solution lies with an invention developed in the 1950s by German engineer Joseph Becker, who devised a way of doing without a traditional ship's rudder. Instead, he designed something called the rudder propeller, a propeller that could turn through 360 degrees and so steer the ship as well as propel it. The modern incarnation of Becker's concept is what enables the world's largest cruise ships to achieve the seemingly impossible: the podded propulsion system.
We have 3 Azipods, each of them are 20 megawatts in size. And 20 megawatts you could translate to being about 200 family cars. It's a huge amount of power, but considering the size of the ship, it's what we need.
The 3 pods actually act like airplane propellers, pulling the ship through the water, rather than traditional pushing-style ship propellers. Combined with 4 times 5,500 kilowatt bow thrusters, they allow the cruise ship's captains unparalleled control. Dials on the bridge allow the pods to be turned to the desired position in an instant, and maneuver the vessels into locations that would have once been impossible.
Well, the Azipods came as a result of really thinking outside of the box. It's ingenious.
But to truly make their mark in maritime history, designers will need to turn to yet another great innovation of the past.
This is a gyroscope, and to explain how it works, we're going to need one of these.
To produce more impossible engineering. The biggest cruise ship on the planet is just 4 months away from completion and launch. The Harmony of the Seas is the latest in a class of ships that eclipses anything that has gone before. Sitting as tall as Tower Bridge, as long as 5 jumbo jets, and as wide as a football pitch. For the project director, Petteri Keiso, it's a dream job.
When I really look at her, I'm amazed always, every single time by the size of the ship. It's big, but it's beautiful, it's awesome.
This mind-boggling structure will hold up to 6,000 guests, making customer satisfaction the #1 priority. A potential challenge when the weather doesn't cooperate.
The clearest issue we have is that the ship is not stationary. It moves, it rolls, it heaves, there's all kinds of movements and acceleration on the ship, which makes it a little bit more complicated.
So how do you keep such an immense vessel steady, so customers and crew can experience a smooth ride, whatever the sea throws at them? Dr. Andrew Steele is finding out how the seemingly magical properties of a classic child's toy provide the solution.
This is a gyroscope, and to explain how it works, we're going to need one of these.
A motorcycle's wheels do more than just power and steer it.
A gyroscope works by conservation of angular momentum, which means that when it's spinning around very, very quickly, it doesn't want to change the direction of that spin. And this can give some pretty counterintuitive effects.
These physical reactions can be extraordinary. An effect known as ghost riding can occur when a bike crashes and loses its rider, but then rights itself and continues its journey. This phenomenal sight is down to gyroscopic forces, such as gyroscopic precession, acting on the bike to try to maintain its original orientation. So how does it work?
Well, I'm going to try and show you with this piece of apparatus here. What we've got is an ordinary bike wheel, but we've filled the inner tube with concrete just to make sure it's nice and heavy. So currently this thing isn't spinning, and that means it hasn't got any angular momentum. And that means it's pretty easy just to make it spin around. It's not very stable. However, if we get this electric drill, we can get the bike wheel spinning. And as we add more speed with the drill, we're increasing that angular momentum. Now it's moving very fast, and now if I give it a whack, you can see this thing is stabilized.
And that's why, in extreme circumstances, a wheel can refuse to lie down. Astonishing as this is, it was the stabilizing effect of the gyroscope that maritime engineers were interested in.
If I get it spinning nice and quickly, I can just balance the spinning wheel on my hand.
Just like a spinning top stays upright, perhaps gyroscopes could do the same for a ship. In 1917, American inventor Elmer Sperry used the effect for the very first time in a large vessel. He equipped the USS Henderson with 2 enormous gyro wheels weighing 60 tons. Inside, 3-meter flywheels spun at an incredible 1,100 revs per minute, creating huge amounts of angular momentum in order to minimize the ship's roll. Although a huge engineering breakthrough, his brute force approach ultimately proved impractical. And as technology has developed, so has the use of the gyroscope.
Over the years, pioneering scientists and engineers have experimented with these gyroscopic forces, to the point where nowadays we can fit tiny gyroscopes on the surface of a computer chip like this one. And they're used everywhere, from mobile phones to aircraft and even ships.
The Oasis-class vessels take the magic of the gyroscope into the 21st century. Instead of the giant spinning wheels employed in the USS Henderson, Harmony of the Seas and her sister ships use a small gyroscope as a sensor, which, via computer, controls mechanical stabilizers.
So in rough seas, what we can use to minimize the roll and the movements of the ship are stabilizer fins. And they are actually fins that emerge laterally from the ship's hull. This is the location we are in now. And what it does, it's sort of like a wing that comes out of the ship. It emerges laterally like this, and then it turns around its axis.
A 20-meter squared stabilizer blade is recessed into each side of the vessel amidships. They're deployed as and when the state of the seas demands it.
Stabilizer mostly counteracts the roll, so the sideways movement of the ship. So if the gyroscopes feel that the ship starts moving this way, it asks the fin to exert force so that it counteracts the movement here, so it tries to always right the ship.
It's now more than a century since the first purpose-built cruise ship set sail on the world's oceans. Now, by drawing from the originators of the past,
Standing next to this 3-4-story tall engine is very impressive.
adapting their ideas, honing them, and making trailblazing innovations of their own, the engineers, designers, and workers constructing the Oasis-class cruise ships are making history.
When first these plans were thought of, I'm sure there were a lot of people who thought that we were absolutely nuts. Absolutely crazy to think of even building a ship this large. But you know, we are not afraid to think large, think big, think outside of the box. And that's what you need. You need a little bit crazy thinking at times to really make great things.
They've succeeded in making the impossible possible.
When we started this project more than 2 years ago, we had only design on the paper. But as we now see it, the dream come true, I feel really proud of what we have achieved.
London. Home to a skyline that boasts some of the world's most iconic buildings. But in 2012, a modern marvel altered this historic vista forever. Two superfans, physicist Andrew Steele and engineer David Knight, are checking out this supersized structure from two equally impressive viewpoints. David, the way most of the city's 8 million residents do, from the capital's streets. And Andrew, with a view normally reserved for the birds.
Wow, look at that. It looks like a piece of crystal, a splinter coming up through the earth.
Soaring to 309.6 meters, the Shard is London's tallest tower.
It's so tall and it's such a prominent part of the skyline that you can't help but notice it.
That's an incredibly audacious piece of architecture and some very impressive engineering.
The Shard's jaw-dropping height is down to owner Irvine Seller's huge ambition and architect Renzo Piano's inspired vision. But it was also born of necessity.
Looking across the London skyline as we approach from the south, you can really see it's just crowded. There's buildings everywhere.
Building in that tight space is a very, very difficult task.
We've got the whole city on our left-hand side now, the Gherkin, the walkie-talkie. We've got all these different buildings crammed into such a tiny space.
In this dense urban environment, the engineering solution to packing massive floor space onto a relatively tiny footprint was to build Western Europe's tallest skyscraper.
Irvine Seller had a dream of building a tall building, a vertical city, and this is the result.
Situated in one of London's busiest commuter hotspots, the jaw-dropping 309.6-metre tower is over 3 times the height of Big Ben. The unique pyramidal facade is made of a staggering 11,000 glass panels, enough to cover 130 basketball courts. Beneath the 60-metre spire lies the spine of the building, a colossal concrete core providing the backbone for 72 habitable levels with over 100,000 square metres of floor space. In 2009, construction on this immense scale posed a career-defining challenge for engineer and project director John Parker.
Building these buildings is always exciting. You're building up taller than anybody's gone in Europe, but this one was particularly difficult.
The dense urban environment would push the team to its limits.
It's in this congested site, just in the corner of a railway station, things going on all the way around it. We had no spare site in which to build it.
It's smack in the centre of London, with London Bridge Station on one side, Guy's Hospital Tower on the other, the Jubilee line of the tube sitting very close underneath. And to add to all of that complexity, there was a building already on this site that needed to be removed before construction could begin.
Removing the former tower's 25,000-ton weight could make the site impractical.
When you put a building on the ground, the very heavy weight compresses the soil. It's like a sponge. It creates a divot where the building is. And when you take that weight off, the ground wants to heave, wants to respond and go back to where it was originally. And time is of the essence. You want to put the weight back onto that ground as quickly as you can.
So how do you construct the tallest tower in Western Europe at speed? And in one of the most sensitive sites in central London. This incredible engineering feat may not have been possible without a great innovation from the past. When it comes to building up, man has always defied the odds.
Well done.
In the deserts of Jordan, the sculptors of ancient Petra carved its vast buildings out of sandstone cliffs,
Very good.
while safely perched on a series of giant stone steps.
Sorry.
Although masonry buildings were rare in Italy's 12th century Bologna, warring noble families looking to build their prestige erected over 100 towers in a city where bigger was definitely better.
Mamma mia, what a whopper.
Perhaps the first skyscraper city was 16th century Shibam in Yemen. Adopting ancient techniques, its engineers used mud bricks to build high-rises that were so impressive, it's known as the Manhattan of the desert. But building these high-rise masterpieces for the modern metropolis would require some subterranean genius. In the 1950s, the bustling Italian city of Milan wanted to build an underground railway system, but was facing two apparently insurmountable challenges. Firstly, large-scale excavations would cause chaos, as engineer Luke Bisbee has come to see for himself.
We've come here to a site where the metro network is being expanded. And being here and seeing the scale of this site, you can imagine the tremendous disruption that would be caused if you tried to do this in the center of the city. Really an enormous challenge.
Poor soil conditions below ground also made tunneling beneath the city streets impractical.
This is actually a really good illustration of one of the key problems here in Milan. We're down here at the bottom of the excavation, and you can see this is an area where they're just getting ready to start to dig a tunnel. And the engineers have gone to really heroic efforts there. Around that wall, you can see they've put some rubber gasket, and they've really tried to keep the water out of the site. But in spite of that, you can see how much water is still flowing in. So these are about the worst conditions you could hope to be digging tunnels in.
It was down to brilliant engineer Dr. Christian Vader to find a solution. The traditional method of creating a relatively shallow tunnel was known as cut and cover.
Let's imagine that I want to dig a trench down between these buildings. And you can see what happens when I do that in this sandy soil. Initially, there's no problem. But if I push just a little bit too far, you can see that eventually I destabilize the soil and my structures will fall into the trench. And obviously that's completely unacceptable on a site in a congested urban center.
To avoid the risk of subsidence and to keep the city moving, Vader turned the idea on its head.
Instead of building one big trench initially, he built two little trenches down the sides of the buildings, and into those trenches he inserted reinforced concrete walls. And these then became known as diaphragm walls.
Vader then built the roof of the tunnel so that the city traffic could resume above, whilst underneath, in the stabilized environment, digging, tunneling, and construction could continue. Instead of cut and cover, Vader's technique covered, then cut. Now known as top-down, this method was adapted all around the world as a way of completing major subterranean projects with significantly less interruption to the world above.
So what Vader achieved here in Milan was to pioneer a really innovative construction method. And it's fair to say that standing down here in one of the new tunnels of the Milan Metro, it simply wouldn't exist without that construction technique.
In 2009, engineers at the Shard were faced with a potentially challenging site and a pressurized construction schedule.
As soon as a project like this starts, you're against the clock every second of the day. Time is money. You need to keep going and keep going quickly.
The solution for engineer John Parker and his team was to build on Milan's innovative underground methods with the added twist of building up.
Normally, a building like this would be built by building a basement first and digging a big hole down to the bottom level of the basement, and then starting the core from that lowest level and building upwards. Now, we built the core on stilts, effectively, that held up the core while we were building it upwards, and then we were, at the same time, digging underneath it and going downwards. That had never been done before. It was an innovation for the Shard.
Incredibly, just 23 of the building's piles would support the structure's central concrete core as it rose from a void in basement level 2. As excavations and casting of the underground floors continued around the pre-sunk columns, the core rose as if balanced on a tabletop above.
This allowed the engineers to shave literally months off this project, and the Shard was built much more quickly and much more cheaply than it could otherwise have been. This really is an engineering marvel.
This audacious twin-pronged approach was an unprecedented achievement. But to complete this super tower, engineers faced more challenges and would have to turn to another of history's great innovations.
The technique that Hagelin developed for this cylindrical shape was absolutely revolutionary for its time.
To produce more impossible engineering. At nearly 310 meters, the Shard is the tallest tower in Western Europe. And today, superfan and engineer David Knight is taking in its jaw-dropping scale from the street. While fellow enthusiast physicist Andrew Steele is getting a privileged bird's-eye view of the already iconic tower.
The Shard is an incredible building. It just stands high, proud above the London skyline. And this incredible bit of architecture really does put London on the map.
The This is a really radical building. It imposes on the London skyline like nothing else. It ascends into the air and the whole thing shines and glistens in the sun. What a stunning sight.
With its luxury apartments, hotel, and 55,000 square meters of office space, this 87-story engineering marvel has set a new benchmark in skyscraper design. But this huge ambition comes at a price. During construction, the £430 million project would require more than 1,400 workers on site. With such high stakes, as engineers tackled the complex concrete core, they couldn't afford to let the schedule slip.
The slow bit of construction is building a concrete core that is the real basis of stability for the structure. It holds the building up, holds the building solid against wind loads, and is a very, very important part of the building. And getting that in place quickly is a real challenge.
And with the central column expected to consume over 10,000 cubic meters of concrete, how do you construct it in record-breaking time? This may not have been possible without a groundbreaking method pioneered in the past. Architectural historian Jen Mason-Garb is in Minneapolis in the USA to find out how an innovation built to satisfy a nation's love of baking ultimately influenced construction methods around the globe.
In the 1880s, Minneapolis was known as the flour capital of the world. Raw grain was brought here from across the northern prairie, processed here, and then shipped across the country and around the world.
But the industry was not without risk. Dry millstones could ignite flour dust, causing catastrophic explosions within the wooden silos. In 1878, the Washburn A, one of the largest mills in the city, was destroyed with the loss of 18 lives.
Grain merchants were facing a storage problem, so clearly a new solution was needed.
The answer would come from a partnership between engineer Charles Hagelin and grain trader Frank Peavy, who together set out to design a more resilient silo with an experimental prototype.
So this is what they constructed, the world's first reinforced concrete grain silo. The technique that Hagelin developed for this cylindrical shape was absolutely revolutionary for its time.
Hagelin designed a wooden cylindrical mould and filled it with concrete. Once the concrete had set, the mould was removed and placed on top of the first section. This process was then repeated until the desired height was reached. Many didn't believe that concrete would hold the volume of grain without collapsing. But when complete, the experimental tower was filled and tested.
So Peavy and Hagelin's experiment worked. They had solved the grain storage problem, and they could take what they learned here and use it all over the state.
Spurred on by their pioneering concept, the result in 1908 was the newly built Washburn-Crosby Elevator 1, part of the Washburn A mill, which at its peak produced over 900,000 kilograms of flour every day.
The most innovative thing about the design are these 15 cylindrical silos, each measuring about 100 feet tall. Constructed by Charles Hagelin, they were the first large-scale concrete grain silos in the US.
To construct the silos, Hagelin built on this sectional prototype, adopting an ingenious new method called slip forming, a technique that allowed him to continually move a concrete-filled mold.
So what we've got here is a simple demonstration of how slip forming works. I've got this bucket of slightly wet sand here. This is going to represent our concrete. And I've got this other bucket here with a hole cut in the top. This is going to represent our slip form. And here's how the process works. A little of the concrete goes in, And slowly, about a few inches every hour, the slip form gets raised up and up. And then I add a little more and raised up a little bit higher.
To reduce the joins and so increase the strength, the rig was continually forced up by hydraulic jacks, whilst the concrete was poured non-stop. It meant that, while the concrete at the top remained wet and fluid, by the time it emerged from the bottom of the moving mould, it had dried enough to be capable of supporting the growing structure above.
The combination of the speed of the rig, how fast the slip forming moves up the structure, and the fact that the concrete has to be poured continuously into the top so that the top layer never fully cures, this is the key to making this whole process work.
The operation was so efficient, it could scale 2.5 meters in just 24 hours, completing a cylinder in around 12 days.
Hägglund's use of slipform construction revolutionized the way that tall buildings are constructed. And today, concrete has become one of the most widely used materials in construction, allowing us to build higher and faster than ever.
Nearly 8 times higher than the Washburn-Crosby elevator silos, the Shard's concrete core would measure 1/4 kilometre. And to construct it at speed, engineers needed a supersized solution. A giant slipform rig measuring 26 by 22 metres.
It was moving upwards at 3 metres a day, almost a floor a day. You have steel shutters which form the shape of the concrete, and then they're moved up almost continuously, 6 days a week, 24 hours a day.
Fed by a high-capacity concrete pump, the system was so efficient it reached the 21st floor in just 10 weeks.
It's amazing to think the first 21 stories of this concrete structure went up before they'd even finished the foundations below.
Still perched on just 23 piles in the centre of the basement, before the core could continue its journey to the 75th floor, it needed more substantial support. This would involve creating Basement Level 3's colossal raft foundation, and the UK's largest ever single concrete pour.
It took 32 hours. We poured the whole thing in one go. It's as much as 3 metres thick in the middle, underneath the core, and it was 5,500 cubic metres of concrete. They had trucks coming in from 3 different concrete plants. It was tremendously exciting to see all that concrete arriving on site.
But completing this mammoth structure would require further innovative solutions from the past.
How do you put that fire out if there's nobody around?
To produce more impossible engineering. In 2012, London's skyline was transformed. As tall as 70 double-decker buses, the Shard dwarfs everything around it. And today, 2 of its biggest fans, physicist Andrew Steele and engineer David Knight, are taking in this game-changing architectural masterpiece from every angle.
This is London's Burj Khalifa, this is London's Shanghai Tower. It was built in very trying circumstances and at speed, and London engineers are really proud of that achievement.
Built from a central concrete core, the tower's unique hybrid superstructure is pulled up around it. 40 floors constructed of steel, 29 stories of concrete, topped off by a monumental 23-story spire at the pinnacle of the building. With his bird's-eye view, Dr. Andrew Steele is under no illusion as to the construction problems posed by the tower's immense height.
When you're building a tower that's over 300 metres high, one of the real challenges is getting the people and the materials up to these incredible heights when you're doing the construction. and the higher the tower gets, the harder that challenge becomes.
Construction had never been attempted before at a building this tall in central London, and it was a real challenge to get men and materials up to the top floor.
So how do you manoeuvre such enormous loads in such a challenging environment? This gargantuan task may have been impossible without another inspired innovator from the past. To construct their colossal pyramids, the ancient Egyptians had to rely on elbow grease and a lot of determination to scale their network of ramps. As cranes were introduced, the treadwheel allowed engineers to use leg power with impressive results.
Faster, faster.
Although only walking pace was recommended. Erecting a giant obelisk in 16th century Rome required more muscle. It would take 800 men to raise a vast lifting tower. Plenty of power to get it up, as long as no one let you down.
Oh dear.
A more reliable solution to heavyweight hoisting would come 3 centuries later. Dr. Rhys Morgan is taking to the waterways of Venice to discover how a seafaring tradition ultimately led to a unique engineering innovation.
Throughout history, this city has had an unshakable affiliation with all things waterborne, and the mid to late 19th century was no different. It was a time of great change in the maritime industry, and old wooden galleys propelled by oar and wind were being replaced by steel-hulled ships and great big engines.
This new wave of heavyweight construction would pose a huge problem for engineers at Venice's historic naval shipyard, the Arsenale. Traditional manually operated cranes weren't adequate for increasingly heavy loads, seriously compromising the Italian Navy's ambitious boat-building program. They turned to brilliant British engineer Sir William Armstrong. His groundbreaking innovation, developed in the dockyards of Newcastle in the UK, would offer the perfect solution to Venice's maritime construction conundrum.
Because of the growing trend of metal hull construction, the Navy decided to commission just the thing for the Arsenale, and here it is. The stunning Armstrong crane.
Completed in 1885, the colossal structure was an imposing addition to the Venetian skyline. And today, Rhys has unique access to its equally impressive historic inner workings.
And the way it works is like this. This huge boiler would generate enormous amounts of steam, and that steam would flow up through the pipework down into these chambers below. The steam drove these enormous pistons back and forth, and they in turn helped pressurize the hydraulic circuit. The water was taken from the lagoon outside, and the pressure from the pistons generated huge amounts of pressure on the hydraulic system itself.
Capable of lifting an unimaginable 160-ton load, the heavy-duty crane transformed the fortunes of the Arsenale.
It was the power that meant that previously unimaginable weights could be lifted, and it opened up a whole new frontier in crane technology.
Over a 30-year period, 9 more of Armstrong's cranes would be installed around the world, heralding a new era in crane development.
By pushing the boundaries of what cranes were capable of, Armstrong created a landmark in engineering history and paved the way for incredible projects that we see all around the world today.
Engineers at the Shard have taken this historic marvel to a whole new level. first phase of the superstructure was tackled using some of the tallest and most powerful tower cranes in the UK.
They started with 4 cranes at ground level. Those went up to about 160 metres. But above that, we've still got 140 metres of the building to go. How do we get the structure, the construction equipment up to that height?
With the building now out of reach of the mighty tower cranes below, engineer John Parker and his team would take an unprecedented step, mounting a tower crane on the rising central core.
What was unique about the Shard was that the tower crane was supported on that slip form. Usually you have to fix the crane to the concrete. We avoided all that so they could both go up together.
As the hydraulic jacks pushed the core and crane higher, the machinery was kept stable against wind speeds in excess of 160 kilometers per hour by extending the lower section of the crane into one of the already cast lift shafts. But despite this ingenious technique, as construction reached unparalleled heights, engineers would have to adopt an even more radical approach.
They then had to use the crane that was attached to the slip form to build another crane which cantilevered off the main building and allowed them to build this final spire on the top of the structure.
This audacious solution elevated the machinery to a staggering 317 metres, the UK's highest ever crane, enabling engineers to lift custom-built steel sections to form the 23-storey spire.
The section could arrive on a truck, they could attach it to the crane, lift it up to the top, bolt it in place, and then get the hook back down to lift up the next section in 20 minutes.
As the tower's spire was completed, around 500 tons of steel had been installed in nearly 100 separate lifts.
The Shard was really going to hit the absolute limit of how high you could build in London.
With the building at its full height, designers could finally start to envisage the monumental Shard. The 40 floors of steel would house around 55,000 square metres of office space. For the hotel and residential accommodation above, concrete was specified for enhanced acoustics and to limit the building's sway. But as well as comfort, engineers had to guarantee the safety of thousands of people, potentially using the building at any one time.
We know from previous fires in tall buildings that it's a real challenge to get people out of the building safely, and that's an absolute focus for engineers working on tall buildings like this.
To ensure the Shard's inhabitants are protected in the event of fire, its designers would need to draw on another great innovation from the past. Professor Luke Bisbee is in Edinburgh, Scotland, as he looks to recreate an engineering marvel that changed the face of building safety around the world.
Now, it might be difficult for many of us today to recognize that fire was once a very serious and everyday threat to our homes and businesses. Heating and lighting were both largely reliant on open flame, and in combination with the fact that many of our buildings were made largely from wood, this is obviously not the best combination.
But in 1874, Connecticut businessman Henry Parmalee developed a system that would help to combat this threat of fire. With largely inefficient extinguishing methods, factories in many US cities were being burnt to the ground. As insurance costs rocketed, Parmalee was determined to control the premiums on his piano factory, so came up with an ingenious form of fire prevention.
So what we're going to do here is try to recreate a simplified version of Parmalee's invention. So what I'm going to do is I'm going to start a small fire here. Any fire in a building is a bad situation. And fires are particularly a problem in industrial buildings of the type that Parmalee was using, because if you have a localized fire, such as this one, that fire can then spread to other flammable contents of the building.
During the night or even daytime shifts, many areas were left unattended, so human detection couldn't be relied on.
So the problem that Parmalee faced was, how do you detect a fire and then put that fire out if there's nobody around? the solution that Parmalee came up with is actually here next to me. And the really critical piece is this little cap right here. And what I have here is a little metal valve, and on the underside of the valve, I have a secondary piece of metal, and we've attached that in this demonstration just with some wax. Now, Parmalee actually used a low temperature melting alloy. What I now have is essentially a valve on the bottom of this pipe that is temperature sensitive. And so the system that Parmalee had invented basically consisted of a reservoir of water. That reservoir is connected through a hole in its base to this copper pipe. That copper pipe runs across and down to the valve that Parmalee had created. And now let's see what happens when we introduce fire into our system. And as I do that, the valve gets warm, and the wax that is holding the plate in place should release the copper plate. And the valve almost instantaneously, sensitive to the temperature, releases water down onto my fire. And so what Parmalee had invented was really the world's first automatic fire suppression system that both detects and reacts to a fire very quickly.
Parmalee would name his innovation the automatic fire extinguisher. Following huge success in the US and Europe, his game-changing piece of engineering genius would pave the way for modern sprinkler systems around the world. Engineers at the Shard have taken Parmalee's pioneering invention and supersized it, incorporating one of the UK's most advanced fire suppression systems.
The sprinkler system is all centrally controlled by a building management system. Total fire engineering control here, getting the water around the building to where the fire is likely to be.
Driven by 200 kilowatt motors, 2 megapumps feed water to 7 sprinkler zones. And 3 pumping stations are located at different levels to ensure even pressure for the building's hydrants. Access for the fire brigade is via 3 firefighting shafts, each including stairs and a fire lift that allows occupants to leave by the same means.
This is one of the first buildings where people can use the lifts rather than just the stairs when being evacuated in fires.
The Shard's safety systems may be cutting edge, but to complete this ultra-modern skyscraper, engineers still faced more challenges and would have to draw on another great innovation from the past.
Without Ellis, the glass-clad super towers of today, which dominate cities across the world, might not ever have been invented.
To produce more impossible engineering. The Shard in central London has rewritten the engineering rulebook. Boasting Western Europe's highest residence, its 95 stories are a mind-blowing sight for enthusiast Dr. Andrew Steele.
It's just incredible. It's this audacious piece of architecture, a splinter of crystal bursting out of the earth in amongst this rammed centre of London. All these different buildings, the Shard just towers above all of them.
And for fellow admirer David Knight, its iconic status is down to one material that appears to seamlessly emerge from the River Thames.
Look at the crazy amount of glass that this building uses. 11,000 separate pieces. It's extraordinary. It just extends above me in a great big ribbon of glass up to the sky.
To build this audacious structure required literally acres of glass, 56,000 square metres, which is equivalent to nearly 8 football fields.
But with little inherent strength, how do you create a tower of glass that's strong enough to stand up, even in the face of extreme weather conditions? This may not have been possible without the great innovators of the past. engineer Dr. Rhys Morgan has come to the city of Liverpool in the UK to see a building which hides the secret of modern skyscraper design.
In the 19th century, as cities like Liverpool grew ever more dense and space for buildings became smaller, architects were faced with a real problem. They had to build upwards, but in doing so, they had to build thicker and thicker walls to support the increasing weight of their structures. So they needed a new engineering solution.
It was local architect Peter Ellis who would provide the answer, designing a new high-rise building using a revolutionary scheme.
This is the Oriel Chambers building, tucked away in Liverpool's financial district. And although a relatively unassuming building, it contains one of the world's most important engineering and architectural blueprints.
Completed in 1864, Ellis incorporated a state-of-the-art frame system, an iron skeleton, able to support the entire building. Ellis did away with the traditional method of building exterior supporting walls. Instead, his iron framework carried the load of the structure on the inside, allowing him to create a non-supporting facade on the outside.
Ellis's iron frame structure not only carried the weight and provided structural stability, but it also opened up a whole new world of architectural possibilities.
Now the walls could be thinner and lighter, and previously unimaginable amounts of glass could veil the building's exterior. Ellis had created the glass curtain wall.
In 1864, it was a really radical idea, and Ellis was criticised by his contemporaries for creating an architectural aberration.
The developers, however, saw the potential. The building's 56 road-facing bay windows over 5 floors flooded it with light, creating premium office space, and 150 years on, the benefits are clear.
It would have been a real luxury to work in here with the abundance of light coming in through these bay windows, or Oriel windows as they're properly called. And to compare it with the building across the street, where the stone construction means the windows are very small, this would have been an amazing place to work in because of the light coming in from all directions. And he also didn't have to use electricity to use lighting in the winter time. A real advanced idea for the 19th century. The fact that these chambers were built in 1864, over 150 years ago, makes it one of the world's first examples of a glass curtain wall installed on a multi-storey office building. And to think that he was derided for it and was so far ahead of his time is quite extraordinary.
However, today it's said that his groundbreaking work on the chambers went on to inspire American architects responsible for the iconic skylines of Chicago and New York.
It's incredible to think that without Ellis's pioneering use of the curtain wall concept, the glass-clad super towers of today, which dominate cities across the world, might not ever have been invented. It's a real masterpiece of engineering.
Engineers at the Shard have built on Ellis's inspired architectural solution to create a standout structure. Its 13 acres of glass curtain walling cloak the entire tower.
What's incredible is that from outside the Shard, it looks like it's a structure made entirely of glass. But actually this glass takes none of the weight. That's all borne by the steel and the concrete structure inside. An incredible piece of engineering.
The steel and the concrete makes the building stand up. That provides the strength and the stiffness, stops it swaying about, supports all the loads. And one of the loads it supports is the weight of the cladding, the weight of the glass.
Unlike the rectangular Oriel chambers, the Shard's extraordinary superstructure allowed its designers to hang 8 sloping facades, defined by the tower's iconic vertical fractures.
It's often called a shard of glass, and the idea was to have a beacon here that would shine out. And this sloping shape is very good at reflecting the sunlight and making it shine.
But creating a vision of glass on this scale called for extraordinary measures never before witnessed in the capital.
The steel superstructure of the building is enveloped by 11,000 panels of glass, each of them weighing 300 kilograms, and the only way to install them was for each of them to be installed individually by a specialist engineer. And looking at it from up here, you can see that's not a job for the faint-hearted.
In March 2012, the fitting of the final glass section would signify a huge milestone for the project.
It is good to be at the cutting edge and driving things forward and doing stuff that's never been done before.
This seemingly impossible architectural dream took less than 4 years from initial construction to its grand opening. The result of brilliant planning, design and testing by hundreds of engineers.
I'm personally excited because I see symbols of London that now include the Shard. It's very exciting to be involved with something like this. It's a one-off, it's a once-in-a-lifetime achievement.
By learning from the great pioneers of the past, adapting, upscaling, and making innovations of their own, engineers have changed the face of skyscraper design.
The Shard isn't just an amazing piece of engineering, but it's captured the public imagination to become a tourist attraction in its own right. And that surely is amongst its greatest achievements.
They have succeeded in making the impossible possible.
The engineers and architects who are involved in designing this building and the people that are involved in constructing it can rightly be proud of what they've achieved. It's an amazing structure.
The Alps, the greatest mountain range in Europe. At its heart is Switzerland, whose alpine routes through the Gotthard Pass form the most crucial transport links across the continent. But Swiss engineers like Renzo Simoni are facing a seemingly impossible problem. In recent decades, traffic has increased tenfold, and the mountain passes are grinding to a halt.
Nowadays there are 1,200,000 lorries crossing the Swiss Alps every year, so we have to do something.
The Swiss solution? To bore a tunnel, the like of which the world has never seen.
This is the biggest and most complex and, of course, most expensive project Switzerland has ever done.
The Gotthard Base Tunnel will be 57 kilometers long and lie almost 2.5 kilometers below the mountain peaks. If Renzo and his fellow engineers can pull it off, it will be quite literally a groundbreaking engineering feat.
This is the longest railway tunnel we are building now here. It's 57 kilometers long, and that means it will be a world record.
But constructing a tunnel of this scale is far from straightforward.
We have many logistical problems. We have high overburden up to 2,500 meters. We have water which is coming inside the tunnel from time to time. We have the rock heat itself with temperatures up to 45 degrees. So there are a lot of challenges.
Since the dawn of time, mankind has felt the need to dig tunnels. Be it for shelter,
There's gold in them hills.
or to mine the Earth's resources. Enemies of the Romans used tunnels to attack them. But even Hannibal had to rely on elephants to make his way through the Alps. Before excavations of the Gotthard base tunnel can begin, engineers face their first seemingly impossible puzzle. How can they see through the solid rock in order to predict the potentially deadly hazards that lay ahead of them?
While tunneling, you have different dangers. It may occur that water comes in under high pressure, big amount of water, so that could be a problem. Or if you have a collapse of the front of the tunnel with material coming down.
Dirk Kruger from Amberg Technologies is a geophysicist facing the challenge.
The normal condition is that we go in tunneling quite blind because nobody has been there before. And the situation is very complex in the Alps. Geology can change from meter to meter.
The extreme depth of the tunnel rules out conventional surveying that takes samples from above. And being unable to predict the geological conditions ahead could be catastrophic.
So if you have a big water-bearing zone, this is the worst case because you have tons of water which are coming suddenly.
The solution to this perilous problem lies in one of history's great inventions. Japan is the most seismically active country on Earth, with roughly 1,500 quakes registered each year. For centuries, little was understood about their cause, nor where they may strike. That was until 1880, when, on a survey in Japan, British mining engineer John Milne experienced a severe quake and began to record their behaviour.
What I've created here is a simple demonstration of a seismograph. I've got a pen attached to a pendulum. When I shake the table and pull the paper through, you'll start to see the pen record the number of shakes on the paper, and that represents the frequency and the amplitude, or the number of times per second of the shakes and the size of those shakes. So let's give it a try. My assistant Kirk here is going to come and shake the table, and as I pull the paper through, you can start to see the trace on the paper, and then if Kirk gives it a really big shake, you can see that increase in amplitude, and then as it calms down, it gets less again. And we can see here where the really big shake was compared to the rest of the time. It's a really simple but quite effective demonstration of how a seismograph works.
John Milne and a team of engineers took this very simple concept and enhanced it, devising the first continuously running seismographs which could detect the epicenter of the quakes in Japan. A design that was taken up and used all over the world. In order to see through solid rock, engineers building the Gotthard tunnel will adapt Milne's innovation and make waves of their own.
Normally the seismographs are monitoring signals in Earth. Here the difference is we create a signal, a small earthquake, which creates waves which are traveling through the rock.
At the VSH Hagerbach Tunnel Research Facility, seismic prediction experiments are undertaken for the Gotthard project. Explosive charges are placed within the rock face. Once detonated, each sends out shockwaves which are measured.
This wave travels through the rock until some condition in the rock changes.
Distinct geological features reflect the waves differently, providing a picture of what lies ahead.
Everywhere where we find these lines, there is an area where we have changes in rock conditions. In water, they travel quite slow. In air, they're more slow. With this system, we are able to have a real impact on the tunneling progress.
Construction begins on history's most ambitious subterranean project in 1996. The route will consist of 2 tubes. And to reduce construction time, the work begins from 4 sites simultaneously, with the ultimate goal that the tunnels will join up underground. But in creating the world's longest and deepest subway, engineers will face many more challenges, and will have to draw on the innovators of the past.
Now this place is really incredible, really amazing.
To make the impossible possible. In the mountains of Switzerland, engineers are undertaking one of history's most audacious construction projects. A 57-kilometer rail tunnel driven straight through the Alps. It will be the longest and deepest ever built, and a feat once thought impossible.
It's really a big innovation to do this. It's very, very tough. Sometimes it's like unbelievable that it's real.
Renzo Simoni is one of the team charged with turning the dream into reality. But they face a series of monumental engineering tests.
It's the longest tunnel ever built. We have, of course, very different geological zones to get through.
So how do you dig a tunnel that far without taking centuries to do it? It's a challenge that would have been impossible without history's great engineering innovators. London, England. Every day, 4 million people descend into a complex underground network of tunnels, more than 20 of which crisscross their way beneath the mighty River Thames. But it wasn't always so. By the early 19th century, Londoners had given up all hope of having a crossing beneath the river, as engineer Professor Luke Bisbee is investigating.
Several previous attempts to tunnel under the Thames had failed, and the problem was the soft and malleable London clay and sand. Hard rock miners had come from Cornwall, but the techniques that they used on hard rock had failed, leading to collapse and flooding. Eventually, it was decided that the project was impossible, and it was written off.
But Anglo-French engineer Marc Brunel, father of Isambard Kingdom Brunel, had a brainwave. As a naval cadet, Brunel had observed the perfect tunnel-like structures left by mollusks called shipworms as they burrowed through timber.
As it digs, this marine mollusk shoves pulped wood into its mouth and digests it. And its bivalve head and hard shell help support the creature as it moves through the wood. The pulp is then excreted as a hard, brittle residue that lines the rear space, creating a tunnel-like structure. The key is to not actually suck all the sand out of the tube. The mollusk then uses its back legs to grip itself to the side of the tunnel and push itself forward into the space that it's created, repeating the process until it finds light at the end of the tunnel. And this
is exactly the process that Brunel sought to emulate.
Brunel's idea started an underground revolution, hidden remnants of which can still be found.
Now this place is really incredible, really amazing. Through a tiny door up at the street, down a rickety old scaffolding, and we find ourselves here in this cathedral-like space.
From this access shaft, Brunel drove the first ever tunnel under the Thames, using his engineering equivalent of the shipworm. A mobile steel framework called a tunnelling shield acted like the worm's hard head, supporting the Earth and preventing collapse. Working in individual compartments, miners excavated just 4 inches before the whole tunnelling shield was pushed forward using screw jacks. A second group of men working behind them would be lining the tunnel with bricks to prevent its collapse. Finished in 1843, Brunel's Thames Tunnel was hailed as the 8th wonder of the world, with almost 50,000 visitors on opening day alone. Today, it forms part of the London rail network, and it all began in this hidden chamber.
Most people would have no idea that it's here, but of course its importance to engineering and to tunnel engineering in particular really can't be overstated.
The Gotthard Tunnel will be more than 140 times longer than the Thames Tunnel, a feat that would be near impossible without Mark Brunel's innovation. In order to chew their way through the Alpine mountains, Renzo and his fellow Swiss engineers are using the modern supersized equivalent.
These machines are really very amazing. You have to imagine it's 400-meter long, the whole machine.
Almost the same length as the Thames Tunnel and weighing 300 tons, these tunnel boring machines, or TBMs, are some of the biggest land vehicles on Earth. So huge, they're shipped in sections and assembled on site.
This is the head which is rotating, and we have about 60 of those discs which are scraping the rock, so it advances like a worm in principle, step by step.
The head turns and breaks chips from the rock, each disc exerting a force of 32 tons. The excavated rock is passed back through the machine on a conveyor. The TBM is then pushed forward into the void on hydraulic legs.
20 years or 30 years ago, it would not have been imaginable.
These mechanical mollusks can munch through 40 meters of rock a day. Behind it, instead of Brunel's bricks, the walls are sprayed with shotcrete, a form of liquid concrete.
Shotcrete is the first safety measurement after excavation and is applied at the walls to assure that no pieces of rock is falling down. With this shotcrete lining, the tunnel is safe.
The giant TBMs carry all the equipment and materials required to bore and reinforce the tunnel. And automation undertakes many of the tasks that Brunel's bricklayers once did. All in all, they measure the length of 4 football pitches stretched end to end. Figuring out the direction to send these mighty machines is its own challenge. Calculating a straight route can be difficult enough on the surface of the Earth. There are trees, hills, and other obstructions to overcome. But it is possible to use landmarks to navigate, or build towers to get direct sightlines. Finding your way beneath the Earth where even the slightest miscalculation could result in disaster is surely impossible.
Getting the TBMs meeting in the middle, it's a very, very big challenge because we have so long distances.
The solution relies on one of the greatest innovations of the 20th century. In 1960, American Theodore Maiman built the world's first laser. Out of basic materials he bought from catalogues. Placing a small ruby within a photographer's flashbulb, he was able to excite atoms, causing them to emit light particles called photons. His creation would change the world, allowing highly accurate measurements to be made over great distances. Less than a decade after Maiman's prototype, lasers were bounced off reflectors on the surface of the Moon, so the Apollo 11 mission could accurately calculate its distance from Earth for the first time. In Switzerland, guiding the huge boring machines will only be possible with the help of lasers. First, GPS is used to map the entire route. But with no satellite signal below ground, each TBM relies on a geodetic guidance system, using incredibly precise measurements to stay on track.
You are measuring the angles and the distances, and this is trigonometry.
A laser theodolite is attached to the tunnel wall and fires a beam at a target on the front of the TBM.
The laser pointer indicates the precise direction, so the commander of the machine always has the control, and he can choose very, very small correction.
But with 57 kilometers of mountain ahead of them, Renzo and the team won't always be able to rely on the massive TBMs.
Let's get out of here.
And will have to draw on more innovations from the past to make the impossible possible. In Switzerland, engineers are undertaking one of history's most audacious construction projects. To reduce alpine gridlock and pollution, they're attempting to build the longest and deepest rail tunnel in the world.
For Switzerland, it's very important to reduce the traffic by freight lorries crossing the Alps.
The Gotthard base tunnel will slice a 57-kilometer route not over the Alps, but straight under them.
With our tunnel project, we bring northern and southern part of Europe closer together.
Cutting-edge surveying guides the giant tunnel boring machines, or TBMs, through the mountainside. But digging a tunnel deeper than anyone has attempted before leaves Renzo Simoni and the engineering team facing another seemingly impossible challenge. One that the TBMs can't overcome.
You can use tunnel boring machines only in conditions where you have hard rock, which is not squeezing. If you have pressure on the machine, it wouldn't work anymore. That would be a problem. So you can use those machines only in very good rock conditions.
Squeezing occurs when the pressure of the mountainside combines with weaker rock types. In extreme cases, it can result in the tunnel closing up again after it's been bored.
Squeezing rock is like if you make a dough at home, and then you put a finger on it and took the finger out, and it tries to close.
If the team use a tunnel boring machine in the squeezing rock zone, the consequences could be disastrous. The solution is to go back to basics, and a technique that would have been impossible without one of history's great innovators. Engineer Luke Bisbee is in Cornwall, on the southwest tip of Britain, exploring an area once critically dependent upon tunnelling.
So it's hard to believe that 200 years ago, underneath the sea, was the largest concentration of submarine tin and copper mines anywhere in the world. And it's been estimated that all told, there's between 50 and 60 kilometers of tunnels out there underneath the waves.
In the 19th century, this tiny county was the world's largest producer of copper and tin, the crucial materials of the Industrial Revolution.
More than 2,000 mines like this one would have dotted the county.
Cornish miners were considered the best in the world, and their expertise was sought in tunnelling projects all over the planet. But by today's standards, their methods were incredibly inefficient. Mostly, the Cornish tunnels were hewn from the rock by hand, the only alternative being primitive explosives.
So this is black powder. This is the world's first chemical explosive.
Better known as gunpowder, early miners would laboriously bore holes by hand in which to lay their charges.
I'm going to light the fuses, and then we should have more than a minute to head down the tunnel. Oh! All right, okay, so let's see what's happened here. Keeping in mind that it would have taken a couple of hours to drill each of these holes by hand, to then put the black powder in and only move that amount of rock, despite a pretty big bang, is a bit disappointing, frankly.
It was not only relatively ineffective, but also dangerous.
The miners would come back thinking that the charge hadn't gone off. The charge would then detonate quite late, and the miners could be maimed or even killed, and in many cases they were.
The invention of a new, more powerful explosive proved even more perilous.
So what I have here is a jar of nitroglycerin, and it was first synthesized in 1847. And you can see just how volatile it is if I take a small drop and place it on this steel plate, and then I hit it with a hammer. So where black powder needs a heated charge in order to coax an explosion, nitroglycerin just needs a small tap. And of course, down a mine, that could spell disaster.
In 1867, it was Swedish explosives expert Alfred Nobel, spurred on by the death of his brother in a nitroglycerine accident, who finally managed to stabilize it and create an explosive that would change the world.
He realized that if he took nitroglycerin and mixed it with kieselguhr, which is a naturally occurring clay-like material, he would end up with dynamite. And you can see that it's quite loose but quite malleable, and it could be rolled to eventually form dynamite sticks.
Nobel's next challenge was mass production. How to safely handle the vast quantities of nitroglycerine needed to make the new dynamite. In Ardea, Scotland, he found a solution.
Nobel really favored this area because of its remoteness, and the sandy soil allowed him to shape the landscape around his factory to protect production workers from potential explosions. It also allowed him to build mounds such as these around us, and on top of these he could place his nitroglycerin production huts.
In each nitroglycerin hut, one man was in charge of monitoring the temperature and another mixed, sitting on a one-legged stool to ensure he kept his focus.
Its sensitivity to temperature and friction meant that nitroglycerin couldn't be safely pumped. And so it was set to trickle down from the huts to the factory, letting gravity do the work.
Once it reached the factory, it was mixed with the absorbent clay before being rolled into sticks of dynamite.
Nobel had created a product that was now so stable that it could be dropped on the ground or even thrown into fires without exploding.
The new dynamite, combined with the invention of pneumatic-powered rock drills, led to a much quicker and efficient form of tunneling called drill and blast.
All right, that's it. Let's get out of here.
And ushered in a new age of mining.
3, 2, 1, firing! Wow, so that was quite something. A lot of power in that one. So we can really see here the power of the dynamite as compared to the black powder. The dynamite has taken that entire mass of rock and thrown it sideways. You can see what a game changer this would have been for the miners working down here.
Wherever engineers at the Gotthard base tunnel encounter zones of squeezing rock, they revert to the tried and tested drill and blast methods pioneered in the 19th century. Only they give the technique a 21st century twist. Specially designed 60-ton drilling rigs, known as jumbos, make the task quicker than ever before.
They are very fast. They need some few hours to bore all the holes needed.
Each 3-meter-long arm has a powerful electro-hydraulic drill to bore holes for the explosives. As one arm drills, the operator lines up another ready to bore the next hole.
The boring jumbo, he's able to make different borings at once. In the past, you only had one and it was carried by man. Productivity of such a jumbo is much higher.
Unlike dynamite, modern emulsion explosives only become active when mixed together at the rock face, making it much safer than traditional drilling and blasting.
So this lorry, although it's carrying the explosive, it's not dangerous because for detonation, you need the 2 compounds. In this lorry is only 1 compound now.
Each detonation takes 8 hours to prepare, making drilling and blasting much slower. But constructing the tunnel without it will be impossible.
The TPM is faster in good rock condition, but if rock conditions are not so good, you come through with this method. If you cannot do it with drilling and blasting, you can't do it at all.
2, 1, go!
Once the team have blasted their way through the obstacle of the squeezing rock, they still have to deal with the mountain's natural inclination to close the new tunnel back up. Tests are done to see if rigid steel arches will hold back the enormous pressure.
We saw that the steel began to deform. We knew immediately that we have to take some countermeasures because otherwise our tunnel would be closed completely.
With the success of the project in jeopardy, the answer lies in an historic innovation. In 1932, engineers Heinrich Toussaint and Egmont Heinzmann revolutionized the German coal mining industry when they invented the TH-yielding steel arch support. Capable of withstanding huge pressure without collapsing, their innovation made it possible to excavate deeper than ever before. Unlike a conventional rigid steel arch, the jointed concentric rings of their design change shape to accommodate the pressure of the rock, rather than totally resisting it.
It's not the steel itself which is deformable. It's the
joint of the steel. All of these joints could move into each other 50 to 60 centimeters without collapsing.
The solution is to bore a tunnel with a wider circumference than is ultimately required. The yielding rings then allow just enough movement to prevent the supports from collapsing, while still resisting the pressure of squeezing rock enough to stop it from closing the tunnel completely. This simple engineering, inspired by the past, is solving a seemingly impossible problem that might otherwise turn the tunnel into an historic failure.
Without this kind of steel arches in the squeezing zone, we would not have been able to build it.
On the 15th of October 2010, after 14 years of digging, boring and blasting, the dream becomes a reality. A TBM crashes through the final few meters of rock, the two halves of the tunnel joining for the first time.
Breakthrough was a very special moment. The last parts of the rock came down and we could see the machine behind.
After excavating more than 114 kilometers of rock, thanks to the laser guidance system, the TBMs complete their monumental job with incredible accuracy.
In the end, they reached a result like this, 1 centimeter vertically and 8 centimeters horizontally, and this was a very, very big result.
With the digging done, a new team of engineers and technicians must now make the tunnel safe for the thousands of trains and passengers who will pass through. A huge challenge that will only be achieved by looking back to the innovators of the past.
Now, this is a place that very few people get a chance to see.
And learning some tragic lessons from history. Due to open in 2016, the Gotthard base tunnel in Switzerland is a true feat of underground engineering.
The breakthrough meant that we have created a world record because it's the longest railway tunnel now. It's amazing.
But the tunnel's monumental scale presents its engineers with one more seemingly insurmountable problem: how to keep the passengers travelling within it safe.
It was one of the biggest challenges to find a tunnel system which guaranteed safety.
With huge volumes of passengers and freight travelling at high speed through a confined space, under 2.5 kilometres of solid rock, accidents could be catastrophic.
I would say fire is the worst case inside the tunnel.
For Renzo and his team, memories of one of Europe's worst road disasters in another alpine tunnel are at the forefront of their minds. In 1999, a lorry caught fire halfway through the 11-kilometre-long Mont Blanc tunnel, linking France and Italy. The tunnel quickly filled with poisonous smoke as the blaze engulfed over 30 vehicles, in an inferno which raged for more than 2 days. Of the 39 people who lost their lives, most died from smoke inhalation. To ensure the Gotthard base tunnel will be one of the safest ever built, its engineers have taken inspiration from the innovations of the past. In the UK, a groundbreaking engineering project below Liverpool's River Mersey changed tunnel safety forever. Professor Luke Bisbee is experiencing it firsthand.
So this is the Queensway Tunnel. And when it opened, it was the biggest and longest underwater road tunnel in the world.
Opened in 1934, it took 1,700 men over 8 years to construct. But it's not the digging of this tunnel that makes it revolutionary.
About 30,000 cars travel through this tunnel every day. And even with modern exhaust systems, that's a lot of fumes. And the engineering innovation in this tunnel is what solved that.
By the early 20th century, while it was possible to build ever longer road tunnels, engineers now had to contend with toxic fumes from the cars using them. In 1930, the decision not to install ventilation until after the opening of Pittsburgh's Liberty Tunnel had left motorists overcome by noxious carbon monoxide. To keep poisonous fumes at bay, the builders of this Mersey tunnel turned to physiologist John Scott Haldane. Famous for introducing canaries into mines as an early warning of deadly gases, Haldane worked on a series of experiments.
And this is what they came up with. It was the world's largest ventilation system. And incredibly, this system is still in use today.
In each of the 6 huge ventilation towers, fresh air drawn in at roof level is pumped underneath the roadway before being blown into the tunnel through ducts along its sides. At the same time, exhaust fans draw toxic fumes out through holes in the roof. The Gorges Dock ventilation tower is home to 6 of the massive fans circulating air through the system.
This one right here is 8.5 meters in diameter. And incredibly, these are the original fans that were first installed down here almost 100 years ago.
Each one can move 100,000 cubic feet of air a minute, safely pumping exhaust fumes from the top of the 60-meter-high tower above.
Now, this is a place that very few people get a chance to see. I'm standing right at the bottom of one of the ventilation shafts.
The huge height of the tower ensures the air supply isn't contaminated by vehicle exhaust fumes from the street.
And it's said that the air down here is even cleaner than the air for the people walking around in the streets of Liverpool.
Once the largest bore ever drilled, the road deck actually forms only the top half of the original tunnel.
Most people, when they drive through the tunnel, they think they're at the bottom, but they're not. Actually, below them is this 2-story high space called Central Avenue.
Designed to house a tram line never built, it now serves as the main air supply duct, where air drawn from the tower is blown into the road deck above.
It's pretty amazing to think that there's this space like this down beneath the road deck. And I have to say, pretty cool to be down here.
With its revolutionary ventilation system, the Queensway Tunnel provided the blueprint for all tunnel design that came after it. The designers of the record-breaking Gotthard Base Tunnel have taken the systems pioneered under the River Mersey and brought them to new heights of sophistication. Electric trains will run through the tunnels so they won't have to contend with exhaust gases. But the potentially catastrophic effect of fire requires a cutting-edge solution.
First aim is that the train leaves the tunnel. If this is not possible, second aim is to get to the multifunction station.
In the event of a fire, trains will either be diverted out of the affected tunnel at 2 crossover points along the track, or directed to one of 2 emergency stations.
These 2 multifunction stations are very, very important for the safety of the overall system.
As a train approaches, the station's ventilation system will be activated remotely from the tunnel control center. Powerful 2.5 megawatt extractors above the track will suck toxic fumes out of the tunnel, releasing it at the surface through an 800-meter high exhaust shaft. As 0.5 megawatt inlet fans replace it with clean air.
The ventilation system can bring fresh air in the tunnel, 250 cubic meters per second.
At each of the tunnel's portals, 6 40-kilowatt jet fans will raise the air pressure in the unaffected tunnel, keeping it free of smoke during the evacuation.
People who have to leave a train come here through the connecting gallery and into the other tunnel, which is not involved in an incident, and wait until a rescue train will come. This system is safer than the rest of the railway network in Switzerland. If you are here as a passenger using the tunnel, you are safer than outside.
Once complete, the Gotthard base tunnel will not only redefine the map of Europe, it will rewrite the rules of tunnel construction. It stands as a testament to the people, past and present, who helped design and build it.
This project will last for generations. It's a project of a generation for more than one generation.
By drawing on the innovations of the past, adapting, improving, and making groundbreaking innovations of their own, the engineers and designers of this incredible tunnel have succeeded in making the impossible possible.
Generations of engineers wouldn't have been able to do this. I am very lucky to have spent 20 years of my professional life together with this project. It's like a part of me.
For much of its history, the submarine has been a deep-water deterrent. But as the face of combat changed during the 1990s, the US fleet was in need of an update.
The Navy was looking to the replacement for the 688 class ships. They were nearing the end of their useful life. Similar to a vehicle, it gets wear and tear over time, and it was time to come up with the newer model.
And what designers came up with would break the mold of maritime engineering.
What we're looking at is the 15th Virginia-class submarine, the USS Colorado. She's 377 feet long. She can dive to depths greater than 800 feet. She can operate at speeds greater than 25 knots.
The Virginia class is one of the most advanced nuclear-powered fast attack submarines ever produced for the US Navy. At the Electric Boat Shipyard in Groton, Connecticut, the 15th vessel of the class is currently being fitted out. For company Vice President Ken Blomstead, it still poses a huge engineering challenge.
Starting with the first ship of the class, it took 15 million hours to build that ship. And with the Colorado, we brought that cost down to 10 million hours. That's the kind of effort that's required to put one of these remarkable ships to sea.
And for the commander of the completed sister ship, the USS Missouri, Fraser Hudson, this trailblazing class is incomparable.
I've served on 3 classes of submarines, and by far the Virginia class is the best engineered that I've had the pleasure of serving on.
First launched in 2003, this technological titan is as long as 26 family cars and weighs in at 7,800 tons, equivalent to 40 blue whales. Equipped with an advanced nuclear reactor, it can dive up to 240 meters, but is also capable of inching across the shallows with pinpoint accuracy, courtesy of a control room equipped with a cutting-edge automated navigation system.
The pilot can literally dial in any depth, any speed. It allows the ship to operate in much shallower water close to shore. The combination of stealth, endurance, the versatility, the range is truly a benchmark for all ships.
In creating this super flexible maritime marvel, the Virginia-class designers have had to overcome several seemingly impossible challenges. Man has endeavored to operate underwater for centuries. Ancient sponge divers would plummet to the seabed with the aid of a weighty rock, holding their breath for minutes on end to retrieve their precious bounty. In the 5th century BC, Greek diver Silas was able to breathe underwater using a hollow reed while sabotaging the enemy Persian fleet. Legend has it, Alexander the Great made the first mission in a submersible craft. Lowered into the Bosphorus Straits in a clear glass barrel, it's thought he spied on enemy sea defences. Being able to actually control a vessel in the underwater world was even less straightforward, and thousands of years on remains a huge challenge. Today, at the 1 kilometre-long David Taylor Model Basin facility in Maryland, budding nautical designers are striving to master submersible design at the annual International Submarine Races.
Scores of young engineers from around the world have brought submarines that they've designed and built with the goal of becoming the fastest human-powered submarine. Challenge is go 100 yards without coming out of the water, touching the bottom, touching the sides, or any part of the submarine falling off.
It may not be a huge distance, but the fundamental task of remaining submerged is no mean feat.
So up and down is a little bit difficult. Left and right so far has been really good. I can follow the line. It's just been a question of keeping the buoyancy right.
Did we make it further than before?
We got about, sort of halfway. The trim is slightly off. Like the controls seem to be working, the propeller's definitely working.
The secret to successful submersibles may still challenge some of the finest young engineering minds. But a huge breakthrough in submarine development was made possible 240 years ago, courtesy of American inventor David Bushnell. Dr. Rhys Morgan is at the Royal Navy Submarine Museum in Gosport, England. to find out about a secret weapon from the American War of Independence.
And this is it, the Turtle, the first submersible used in recorded underwater combat. Bushnell's plan for the Turtle was to sneak up on the British enemy ships moored in New York Harbor. The vessel had lots of weights in it to help it sink into the water, and underneath the base there was a ballast tank which would be filled with water. And the operator, a man called Ezra Lee, would pump the water in and out of the tank to help sink to the right depth.
As the Turtle slipped underwater, its two surface-mounted snorkels would become sealed, leaving the pilot with a limited air supply, as he powered the craft using his ingenious hand-cranked front-mounted propeller. As he approached his target, his mode of attack was even quirkier.
The Turtle's weapon, a keg of gunpowder, was attached to the back of the wooden hull. As the submarine silently crept up underwater to the base of the ships, it would be attached by this drill, which would be literally hand-drilled into the base of the ship.
Unfortunately, the pilot Ezra Lee hadn't banked on the British fleet being equipped with a metal hull.
By sheer bad luck, Ezra Lee wasn't able to drill into the ship's hull, so the Turtle was a bit of a failure. But having said that, it did set the precedent for submersible combat, and the principles of ballast tanks and propulsion still to this day remain on all submarines.
Unlike the one-man Turtle, the Virginia class can hold up to 135 crew. As ship's manager Patty McDaniel fits out the class's latest vessel, conditions are less cramped than on board its historic predecessor, but still tight, and ingenuity is called for.
One of the challenges with the design of the Virginia-class ships is all of the services and equipment that we need to fit into a tight space. So all through construction, we try to design having spaces to put all of the services up in. One of the other challenges with that is the crew when they come out to sea. These racks are the extent of the space many of the crew members have to store all of their items. So just this thickness deep is what these sailors have to have all of their clothing and books and whatever they choose to take out to sea with them.
And this compact theme continues on board, whatever the rank.
This is the wardroom of the Virginia-class submarine. So the wardroom, as you might imagine, is where the officers gather to eat. Among other things, it's also where a lot of the meetings happen to discuss all of the ongoings on board the ship. Interestingly, too, submarines are very limited on space, so the table is a large clear surface, so this doubles out at sea as if you needed to have an operating table.
When these super subs are in service, they can dive significantly deeper than the hand-pumped submersible Turtle. Their ability to reach depths of 240 meters is down to a sophisticated system of internal and external ballast tanks, capable of holding gallons of water.
We have 5 external ballast tanks that are normally filled with air when I'm riding on the surface. When it is time for us to dive, we'll open vents on those ballast tanks. There's grates on the bottom of the ship that allow water to come in, displace the air, making the ship just slightly negatively buoyant. We then proceed down to the depth that we want to go to. And we use internal ballast tanks to make the ship neutrally buoyant, but then we can progress on our way whatever depth we choose.
Faced with a variety of missions, the crew on board the Virginia class have an abundance of cutting-edge controls. one of which has replaced the most iconic feature in submarine history. The periscope has been the sub's eye to the world since the late 19th century, but engineers have taken the bold step to substitute it for a state-of-the-art photonic mast.
The photonic system is a mast with a sophisticated camera system that allows what would normally be displayed just in a periscope to be displayed on widescreen monitors throughout the ship.
I used to have an optical periscope that came down, which drove the construction of the submarine and the orientation of all of the rooms on the submarine.
Traditionally, the bulky structure of the periscope forced the control room into a cramped upper deck. But on the Virginia class, the compact imaging equipment is only housed in the part of the structure known as the sail, allowing the sub's nerve center to be located on the wider second deck.
My control room that I'm standing in right now houses all of the important decision makers. It really brings the crew together to operate as a team, as a unit.
The Virginia-class designers are pushing nautical boundaries. But to make their mark in maritime history, they face more challenges and have to draw on innovations from the past.
Wow, look at it. Look how smooth the flow is off the stern as it passes through that dive field.
To produce more impossible engineering. The $2.7 billion Virginia-class submarine is the US Navy's most advanced attack sub. The 15th vessel of the class is currently under construction at Groton, Connecticut, and ship's manager Patty McDaniel is in no doubt about its engineering pedigree.
What we have now on Colorado really incorporates the latest and greatest of what's out in industry. We're always improving, we're always getting better, and we'll continue to evolve.
I really believe Virginia-class submarine has set a benchmark for marine engineering. The designing and building the Virginia-class was a continuation of all the great work we've done for over a century.
Unlike many of its historical predecessors, the 115-meter-long streamlined sub is built for a wide range of missions, including reconnaissance and surveillance. A sophisticated system of sonar arrays allow it to map its way across the ocean floor, propelled by a virtually silent advanced propeller known as a propulsor.
The ability to put literally tens of thousands of horsepower into the main engines, into the propeller, and yet be so quiet. The level of technology required to do that is amazing.
Warship bearing 054, range 1,000 yards.
The Virginia class is acoustically the stealthiest submarine that the US Navy has ever produced.
But as well as remaining undetected in the world's oceans, the submarine's flexible remit also calls for speed and maneuverability. So how do you construct a streamlined hull capable of cutting through the world's oceans? To achieve this, the Virginia-class engineers looked to one of history's greatest nautical innovators. Until the end of World War II, submarines were essentially surface ships with the ability to dive for a maximum of 48 hours. Underwater, the vessel became relatively cumbersome and inefficient. To improve performance would need a total rethink in submarine design. Naval engineering professor Matt Werner has come to the Webb Institute of Naval Technology to see firsthand how engineers came up with a solution.
So here we have our World War II submarine. And if we compare it to this model of a surface ship, we see a great number of similarities. This hull form is really about
traveling on the surface.
Its sleek design creates an extremely low bow wave, resulting in a small wake and low resistance, all perfect for minimizing drag on top of the water.
When we take the same hull form and place it below the water, we pay a penalty for this type of hull shape.
Surface-mounted equipment and an uneven hull shape create both frictional drag between hull and water and form drag, as water separating from the hull causes resistance-inducing eddies, dramatically reducing speed. To create a submarine that was more efficient beneath the waves was a design conundrum. The solution would be down to charismatic Admiral Charles Mompson. The US naval officer would commission over 25 large-scale models with the sole intention of creating speed and performance underwater. Finally, all of his testing paid off.
Those models ultimately resulted in the teardrop hull form that became the standard for all modern submarines.
To appreciate this game-changing design in motion, Matt is injecting dye into the tank to analyze its hydrodynamic qualities.
So we've got the model in the water now. We're towing it below the surface. We put dye in front of it, and the model will pass through that dye field. And hopefully what we'll be able to see is some nice smooth flow across the stern of the model as it passes by. So let's see how it goes. Okay, so it's coming into the window now and right into the dye field. And the bow goes through the dye. And wow, look at it. Look how smooth the flow is off the stern as it passes through that dye field. That's showing me we have very low resistance.
With an even, rounded, streamlined shape, the teardrop hull dramatically reduces both frictional and form drag. And in 1953, the culmination of this groundbreaking work was an engineering masterpiece.
So after countless hours, tests, and calculations, Admiral Munson and his team had done it, and this is the result. The USS Albacore.
The revolutionary Albacore changed the face of submarine design.
By getting away from that ship-type hull form and going to a true submerged-type hull form, we have the fastest thing in the water, the most maneuverable sub ever to that point, and the baseline for all subs to come.
Over 60 years after the Albacore first set sail, the US Navy's Virginia class still adopts Admiral Mompson's game-changing teardrop hull.
We need to have very strict circularity requirements to ensure the hull sections are very circular. And when we join them together to form the pressure hull, they must be extremely straight so that our travel through the water uses the minimum amount of energy.
At the Rhode Island Manufacturing Center, modern construction techniques have taken hydrodynamics to an unprecedented level.
We have 3,600 dedicated men and women who take raw steel plate, pipe, and cable and create completed 2,000-ton modules. Raw steel plate is brought in, cut machines automatically cut the plate to the right dimensions. In the case of pressure hull structure, it's rolled to get that circular shape for the pressure hull.
It takes 5,000 tons of force to form the robust steel into the iconic submarine shape. Engineers then adopt a sideways approach to fitting out.
Hull cylinders are turned axis vertical and outfitted with structural shapes like internal tanks, and large piping assemblies. It allows us to use cranes and vertical picks to drop those assemblies in and more cost efficiently install them.
Each of the cylinders are then placed horizontally, allowing outfitted decks to be slid in. Before the completed modules are shipped off in preparation for final assembly. A process that never fails to impress ship manager Patty McDaniel.
When you pair up the last hull section and you actually have the ship look like a whole ship together in a bay, it's really exciting to see it all come together.
And transporting this monumental structure to its natural habitat is no less impressive.
We actually have 78 of these transfer cars moving in unison. It's one individual flipping one switch and all of the cars start moving together. And it drives the whole ship out along the tracks on the floor, right out to the pontoon, and we float off.
This giant of the deep is taking engineering into uncharted territory. But to create one of the most advanced submarines in history, its designers need more inspiration from the past.
This is an incredible moment. What an amazing feat of engineering.
To produce more impossible engineering. The US Navy's Virginia class is pushing the boundaries of submarine design. Program Vice President Ken Blomstead has been at the heart of its engineering since 1996.
When I saw the original requirements for the Virginia class, there were several requirements that I thought were pretty challenging. But as we started to build the ship, it really came together and turned into just a great platform.
"115 meters in length, each sub is made up of just 4 supersized modules, but contains around 1 million components and requires 10 million man-hours to build. Engineering on this epic scale is an awe-inspiring experience for ship's manager Patty McDaniel.
It's really been amazing seeing these systems that I did the calculations on be built and tested and then actually eventually go out on sea trials. It's really a privilege to be able to see it all come together.
For the crews on board, a key to the success of each mission is the ability to stay underwater for prolonged periods of time.
This crew of 135 sailors have to be able to go anywhere in the world, deploy from their home port, and be operating in any ocean and not be concerned about the amount of fuel consumption that they're using.
So how do you propel a submarine to the most remote parts of the globe without having to refuel? This seemingly inconceivable task would not be possible without another innovation of the past. Early submersibles relied entirely on human power for propulsion. In 1620, there are accounts that Dutch engineer Cornelius Drebbel
down we go.
Submerged a fully crewed vessel into the River Thames and then rowed it from Westminster to Greenwich.
And stroke.
Although historians now believe a semi-submerged tidal drift may be a more accurate version of events.
Useless.
In 1863, the first mechanical submarine was launched, running on compressed air. The Plongeur had an impressive top speed of 4 knots,
Ooh la la.
but had to be incredibly long to house its 23 air tanks, and needed a support ship to top up supplies.
Ow! Watch it!
cracking the huge problem of submarine propulsion would be down to one of the most colossal scientific discoveries of all time. Dr. Rees Morgan is at a secret decommissioned location in Austria to discover more.
This is a nuclear reactor, the core of a nuclear power plant. The core itself is a whopping 20 meters deep. If up and running, this reactor alone would produce enough electricity for 1.8 million homes. This is an incredible moment. What an amazing feat of engineering.
The world's first peacetime use of nuclear power occurred when the US government switched on the experimental breeder reactor in Idaho in 1951. It temporarily powered the town of Arco and paved the way for domestic nuclear power. But Captain Hyman Rickover of the United States Navy had other ideas. He recognized the potential for harnessing this power and using it in a submarine.
Rickover was an incredible pioneer. The problem with powering submarines is that most forms of power for propulsion require air, so the submarines had to resurface. Or the alternative would be battery, but they just didn't last.
Despite flying in the face of popular belief, Rickover was convinced that the fundamental process of a nuclear reaction to boil water and create steam could provide a groundbreaking solution.
Nuclear reactors are just very large ways of boiling water. And here I've got a steam cleaner that's going to represent my nuclear reactor. I've got some water, and when I pull the trigger, it boils the water, turning it into steam. As I direct the steam towards my turbine, it starts to generate electricity, and that turns on my light. The difference between my little reactor here and this enormous one here is in the way that the water is heated. And the answer lies at the very heart of the core itself. Nuclear fuel rods contain thousands of uranium pellets, and it's the uranium atoms that split, causing a chain reaction that generates vast amounts of energy in the form of heat. The result is an almost limitless supply of power that can keep on producing for years. The problem Rickover faced was scaling down something as huge as a nuclear reactor down to the size of something that could fit into a submarine and still provide the power.
Rickover's solution was the world's first pressurized water reactor. The core inside his super-efficient reactor vessel heated a loop of pressurized water. This, in turn, vaporized water in a secondary loop, creating steam to drive the main turbine, producing electricity. After vigorous testing, in 1954, Captain Rickover watched as the Nautilus was launched. A pioneering nuclear vessel that would travel 1,300 miles in less than 90 hours, fully submerged.
This was a huge game changer in submarine engineering. Previously, submarines could only stay underwater for up to 48 hours. Now there was absolutely no need to resurface. Rickover and his incredible engineers had made the impossible possible.
The pioneering Nautilus's reactor only had to be refueled every 2 years. But the Virginia class has taken this pioneering technology to an unimaginable level.
The Virginia-class submarine has a life of ship core. It never needs to be refueled. Previous submarines had to be refueled during its life.
The Virginia-class submarine is powered by a nuclear reactor that has been designed to last the life of the ship for all 33 years.
Converting seawater to steam, this top-secret reactor plant is capable of powering the vessel for over 1.5 million kilometers without refueling, as well as generating all the electricity on board the sub.
The ship has amazing capabilities. In fact, the only limiting factor for me when I go to sea is the amount of food that I can bring on board. The nuclear power provides us the ability to operate anywhere in the world, in any ocean environment.
And astonishingly, its unlimited power source also allows the vessel to hover motionless in one location for weeks at a time.
The reactor on the Virginia-class is the most advanced reactor that the U.S. Navy has produced.
But sustaining over 130 crew underwater in a sealed vessel for months at a time requires yet more inventions from the past.
We're about 5 minutes in now. We're really starting to use up the oxygen.
To create this impossible engineering. For over 2 decades, an army of designers, engineers and workers have been creating the Virginia-class, one of the most sophisticated subs ever built for the US Navy.
It is wonderful to wake up every day, to come to work. Everyone takes a lot of pride in what we do, and it's a joy to see it come together.
12 super subs are now in service, each equipped with a state-of-the-art nuclear reactor that allows the vessels to remain underwater for months at a time. But keeping the crew safe for these prolonged periods, as much as 240 meters below the surface, poses a huge challenge.
In the submarine, we have an enclosed environment, and so we have to monitor the atmospheric controls on board and the levels of the oxygen, the carbon dioxide, and other trace gases to make sure that it remains habitable for the sailors.
So how do you keep over 100 crewmen alive for months at a time? The answer lies with the work of a genius chemist over 200 years previously. To appreciate the problems of creating a human habitat underwater, Dr. Rhys Morgan is being put through his paces at a naval test facility in Portsmouth, England.
This is a hyperbaric trials unit used by navies around the world to test undersea and high-pressure systems. This HTU can uniquely recreate the kind of immense pressures experienced by submarines at the very bottoms of the ocean.
Rhys is using this technology to put himself in the shoes of the early submariners, to experience just how quickly the atmosphere on board could change.
This is a potentially dangerous experiment, so I'm here with Jules, who's going to look after me inside the chamber. Outside, there's a whole team of medics looking after both of us. This is a completely sealed unit now.
Rhys and his crew now replicate the physically demanding work on board an operational submarine.
It's amazing how you do start to feel slightly more out of breath than if you were just outside on a normal exercise bike.
CO2 makes up just 0.04% of our normal atmosphere, and in this quantity is completely harmless. But in a sealed unit, the level builds as we exhale and can become dangerously toxic.
We're about 5 minutes in now, and we've already created half the maximum permissible CO2 levels in the chamber. So we're really starting to use up the oxygen. A bit hot. Okay.
After nearly 6 minutes in the chamber, the oxygen and CO2 levels have become completely unbalanced, and it's considered too dangerous to remain inside.
Exhausted. I don't know how those early submariners did it. I could really feel the oxygen content lowering and the carbon dioxide increasing in there.
Submarine engineers of the Second World War would tackle increased carbon dioxide levels by chemically scrubbing it. Large quantities of soda lime spread around the sub would react with and absorb the CO2 in the atmosphere. But by far the bigger challenge was how to replenish oxygen levels in a completely enclosed vessel. The answer lay as far back as the early 1800s, through the work of an English chemist, William Nicholson. Inspired by the invention of an electric battery, Nicholson had the idea of placing battery leads into water. In doing so, he produced a chemical reaction, what we now know to be electrolysis.
This is a simple demonstration of electrolysis. I first have my water for the electrolyzer. Okay.
2 water-filled test tubes are placed over the submerged negative and positive electrodes before the electrical current is switched on.
And you can start to see immediately the gas bubbles forming on the electrodes here. The negative electrode is generating hydrogen and the positive electrode is generating oxygen. And so each of these jars now has displaced the water with the gas.
This reaction is caused by the positive and negative electrodes attracting and separating the oxygen and hydrogen molecules in the water.
Now what we're going to do is test the purity of the gas. And this jar here has got oxygen in. And if I blow this splint out, with the pure oxygen inside, it should glow. So there we have it. We've produced, in just a few seconds, enough oxygen to fill this test tube. What we need to do in a submarine is to scale up this whole process to provide enough oxygen for all the submariners deep beneath the waves.
The engineers of the Virginia class have built on this groundbreaking work to provide life-sustaining conditions under the water for months on end.
In order to maintain that environment without coming up for more air, we create oxygen through electrolysis. We have pure water, we then use electricity to split the hydrogen from the oxygen. We distribute the oxygen throughout the ship and then remove the hydrogen so that we can maintain levels right at 20%, just like normal air.
Located in the sub's auxiliary machine room, the US Navy's Advanced Integrated Low-Pressure Electrolyzer has a maximum capacity to create over 200 cubic feet of oxygen per hour. The potentially toxic carbon dioxide is removed by a sophisticated amine-based removal plant.
You expel carbon dioxide and that builds up in the ship. I have atmospheric control equipment on board that absorbs that carbon dioxide. I then compress it and can either store it or discharge that as well.
Although the crew on board experienced normal living conditions, when working up to 240 meters below sea level, all-round safety is a huge consideration, and every eventuality has to be prepared for.
In the unlikely event of a submarine sinking, we definitely have the capability to escape.
In case a sub's internal atmosphere is ever compromised, Chief Warrant Officer Eric Nabors trains submariners to perform a pressurized escape in an ingenious piece of equipment known as a size suit.
It's designed to provide the occupant fresh breathing air through the compression and ascent phases. It provides 75 pounds of positive buoyancy in the water. It travels at 625 feet per minute through the water column.
Topside, request permission to fill and equalize.
You have permission to fill and equalize.
As the regulated lifting force of the suit propels the students safely through the 37-foot escape trainer, they must follow one golden rule.
The number one rule of submarine escape is never ever hold your breath. Because the escapee is breathing compressed gas at depth, and they travel through the water column, the pressure around them decreases. We are concerned with pulmonary overinflation syndrome.
This potentially fatal condition could lead to the rupture of air sacs within a crew member's lungs.
If a student were to hold their breath, that would occur. So we teach them to breathe normally or exhale the entire way to the surface.
Incredibly, in open water, these technological marvels can withstand up to 250 pounds of pressure per square inch.
These suits have been tested to depths up to 600 feet of seawater. The size suit itself is an incredible piece of engineering.
It's now more than a century since the first self-propelled submarines plunged into the depths of the oceans. Now, by drawing from the innovators of the past, adapting their ideas, upscaling them, and making trailblazing discoveries of their own, the engineers, designers, and workers constructing the Virginia class are making history.
Come down the waterfront, to see these submarines being built, to see the crew starting to take over system by system as we turn it over to them and bring the ship to life. It is truly a magical thing.
The Missouri just returned from 6 months of operations, and if you could imagine driving your car for 6 months straight, 24 hours a day, it's truly a testament to the engineers who designed it, the people who built it, and those 135 sailors who operate and maintain it on a day-to-day basis.
They've succeeded in making the impossible possible.